Sometimes I get going and I just forget. I'm glad I didn't forget completely.
That's
Okay.
the trouble with getting old.
Oh, I know. And you get excited too. Okay, so in a series circuit, your resistances add together. So R total is equal to R1 plus R2 plus however many you have. In a parallel circuit, again, your total resistance is equal to R1, R2 divided by R1 plus R2. And again, impedances behave just like resistances. You can add them if they're in series, and you can do the parallel combination if they're in parallel. And two 100 ohm resistors in series would be 200 ohms. If I were to change those to, let's say, 8 ohms and make them speakers, what would my total resistance be? 16 ohms. Okay, now what if I were to take this other circuit over on the right-hand side, and I were to say that I had two 8 ohm resistors. Actually, we're going to erase that part. There we go. Okay, if I have that, and now that's two 8 ohm resistors, what is my combination equal to? How many ohms?
4 ohms.
4 ohms. Okay, this is actually really important when you're dealing with audio circuits, because if you have speakers that are in parallel, you actually get less resistance, which means that your amplifier, because it turns out speakers, they do have a little bit of resistance, but basically if we look at what a speaker is, it looks like this. What is that?
An inductor.
An inductor. And the way that a speaker works is that there's basically an inductor, and coming through the center of a speaker is this permanent magnet, which is attached to a diaphragm, which basically moves air back and forth as it moves back and forth. So what does a speaker do here? As it moves back and forth and the diaphragm moves air back and forth, what does it make?
Produces sound.
It makes sound. Okay. But now what is the actual resistance of a coil of wire? Very small. It's just basically a coil of wire, but it's an inductor, is it not? Which means that it actually has an impedance. So the impedance of a speaker would typically be listed as something like 8 ohms. And in fact, if you're listening to a speaker right now, which I'm assuming you are, it probably has an impedance of 32 ohms or 16 ohms or something like that. My headphones are probably 32 ohm impedance speakers. That's also why, depending on how you wire things up, if you get current division going through each of two different speakers, you notice that both speakers get quieter than just the one. The reason being that when you get to that node right there, the current has to split. Well, you get, let's say, half of the current. And what's the formula for Ohm's law again?
E equals I times R.
That's 1/2 of it. What's the other one?
E equals I times E.
Yep, E equals I times R, and P equals I times E. Okay, so if our resistance splits it, if our resistance is such that our current is split in half, then what ends up happening to our power going through each speaker? If our I gets cut by a factor of 2, what happens to our power?
Drop
It's
6
down.
dB.
Yep, it drops by a half, right? Which for power is actually 3 dB.
3 dB. That's right.
That would be
I was
so
thinking
basically
voltage.
your speakers would each make 3 dB less energy. Okay. Now, this also is very important because let us say that we have a circuit where we have a resistor and another resistor. And let us say that those resistors are light bulbs. All right. Now, what that means is that you have the same current flowing through everything, and you have R1 and R2. The same current, I, flows through everything, which means that you're going to have the same current. Well, it also means that your voltage, let's say that this is E, this is E1, and this is E2, they're going to be different because of Ohm's law, which means that P is equal to E times I, and your voltages are going to be different. So that means that your power is going to be different, which means that if you were to make a circuit like this, what happens to the power of each of those things, each of those resistors? They're going to be different. What if they're light bulbs? What does that mean?
One will be brighter.
One will be brighter than the other. Yeah. Do you want that in your house? The other thing is, what happens if one of those light bulbs is removed or blows out for whatever reason and becomes an open circuit and now looks like that? What happens to all the other lights in your house?
Everything goes out.
Everything goes out. This is your classic Christmas tree strand of lights. And that is why we don't wire our houses that way. That is why our houses are wired like this, with everything in parallel all the way back to the breaker panel, because then you can remove something and everything else keeps working. Also, it's also important to note that you have the same voltage E, which actually I'm going to use a sine wave here because that's what's coming into our house. You have the same voltage everywhere along this bus, plus or what, give or take a little bit for resistance in the actual wire. Now, what it also means is that this main bus wire right here is going to be carrying all the current necessary to run what?
Everything.
Everything. That's right. Every single thing in your house. So this, it turns out, might be a 15 amp circuit, and this is a 15 amp circuit. And even though there's nothing hooked up, this is a 15 amp circuit. So how much current does that wire have to be able to carry?
45 at least, eh?
45 amps at least. That's right. So this might be a number. This might be a number 14. This might be a number 12 wire. This one might be a number 12. Those are known as AWG, which is a wire gauge. This right here is probably like a number 6. So it's a much heavier wire. And that is your main bus wire that feeds everything in your breaker panel. And some houses might have enough of them that your main circuit breakers, the actual bus is set up for 200 amps. At that point, that's not even usually a piece of wire. That's usually just a solid bar of copper at that point. And the wire coming in from the utility might be like 3/0, which is a very, very, very heavy cable. So how does the power company avoid having to carry that kind of current everywhere? What do they use again?
Transformer.
Transformer. And they have lots of turns on their side and very few on your side, which means that 120 volts on your side or 240 volts on your side as it comes into your house quite likely translates to 7,200 volts on their side, which means they don't have to carry as much current. Okay, I think the time has come for us to start talking antennas and feed lines. I believe it is. Yay, my favorite part of the whole class. Okay, we're talking antennas and feed lines. Okay, so we already covered polarization a little bit. Does anyone remember what polarization is?
Orientation of an electric field.
That's right. So that's polarization. Okay, if I have something that's parallel to the ground, what would the polarization be?
Horizontal.
horizontal. If I have something that's vertical, the polarization would be
Vertical.
vertical, right? Because it's the direction of the field and it's actually generated in parallel to the wire that's making it. So we have vertical polarization and horizontal polarization. Now you can also have polarization that continually changes direction, and sometimes it's going up and down, and sometimes it's going side to side. Any guess as to what that's called?
Elliptical.
Elliptical or circular, depending on whether or not it's symmetric, and it's continually rotating. And in fact, if it's circular polarization, then there's actually a right hand and there's also a left hand, depending on which way it's turning. But you don't have to know that for this class. All right, so a half wave dipole. So remember yesterday we were, or actually 2 days ago, we were talking about wavelengths. So this is a wave. And what's a feature of this wave? What is this thing called? The total length that it covers?
Wavelength.
Wavelength.
Wavelength, sorry.
Okay, excellent. And what is the little symbol that we give to wavelength? Does anybody remember?
Lambda.
Greek
Yeah.
letter lambda. Okay, and we measure this in meters. Okay, so this is actually now going to become really, really important, because what we started with is something that was, you know, sort of like a metaphysical thing traveling through space, but it's an actual physical thing now. Well, now we're going to figure out exactly how we make it. So there are a couple of different antennas that we like to use. Well, so what we're going to do is we're going to take this and we're going to cut it in half. That is a half wave. So I'm going to ask now a very important question. If this is a piece of wire and it's a half wavelength long, what is the current, if I have a current flowing, what is the current at this end of the wire and at this end of the wire?
Whatever it started out being.
Nope. Think about it.
Zero.
Think about it. Can you
Know the
have a
resistance of the
current
wire is?
flowing? Can you have a current flowing if it has nowhere to go?
Oh, no.
No. So the current at the end of a wire has to be zero. It absolutely must be. That is a condition that's set up by physics. Basically, if you have an electron flowing in this way and there's no accumulation, it has to be matched by an electron going back the other way. By something called Kirchhoff's current law, all the currents going into a node have to equal zero, right? I define this as a node. I can define this as a node, which means that the current flowing that way has to be equal to the current flowing that way at any given point. Well, in this particular case, I've defined it so that my node is all the way at the end. So it only has one way to go. So my current has to be zero at those points. Okay, this is actually really important, because if the current has to be zero and it's a half wave long, and I can now project this half wave onto this thing that I drew, which is a piece of wire, it has to be zero at the ends, and it has to go up here to the middle, and it has to come down like that. Okay, so that by virtue of that, what is my current right here at the middle? Is it minimum or max? It has to be maximum,
It has to be mixed because it's the,
because it has to be. Well, as actually with antennas, with wires, as it turns out, my current and my voltages tend to be opposite. So my current maximum translates to approximately my voltage minimum. So that's my voltage. This is my current. And now we're going to go back to Ohm's law. Ohm's law, what's Ohm's law again?
E equals I times R.
E equals I times R. But in this case, we're actually going to replace R with a different letter. We're going to use that Z again. We can use them actually. The resistance, as it turns out, is a is a degenerate case of impedance. Impedance actually includes resistance, believe it or not. So, and the reason being that impedance is actually equal to R plus JX on a complex plane, which I can get into later if anybody wants to. We'll call that enrichment activity. I can talk about that at the end of today if you want.
I do not want to be in it.
But
That's the-
anyway, it's actually very interesting. They're actually perpendicular to each other, and you can have resistance with no reactance or reactance with no resistance. But anyway, what we're going to say here is E equals I times Z, because an antenna at the feed point actually has impedance. So we're going to look at a couple different points. We're going to look at right here, and we're going to calculate E I Z, make our circle. We're going to cross out the Z. So Z is equal to E divided by I. So we're not looking for actual numbers here. We're looking for what your gut feeling says, given the fact that we have a voltage and a current at every point. So looking at the center of the antenna right here, Z is equal to, is our current going to be big or small?
Big,
Big.
pardon me,
Okay,
should turn the other way.
turn the other way. Okay, our current is going to be big. Is our voltage going to be big or small?
Small,
Small.
Okay, so if we were to look at this qualitatively, what's small divided by big? It'd
smaller,
be small. Yeah, we'll just call it small. So that would be a low impedance. How about if we did it all the way at the end? What's our
Okay.
voltage? It's going to be big.
big,
And what's our impedance? What's our current? It's practically zero,
Zero.
right? What's something that's big divided by something that's small?
big,
Big. So qualitatively, what this means is that we have a high impedance at the end and a low impedance at the middle. Well, if we're trying to push power into a thing, which is it easier to push power into? A high impedance or a low impedance? Low impedance. And so what that really translates to is the fact that we now have this thing, which is a resonant antenna, and it's very easy to feed power into, which is known as a half wave dipole.
A what?
A half wave dipole. I didn't draw that very well. Right? It's a half wave dipole. And what we do with this dipole is we take this center point and we split the wire right here. We split the wire right in the middle. And this is the first half of it. And this is the second half of it. And we basically take this feed line and we run this to our center and this to our shield of our cable. And these basically will now have equal and opposite currents as you have power going up and going down. And what that does is that it actually ends up making the picture that you see up there right here of all the currents and voltages. And because it's fed at the center and the current is still zero at the ends, it's maximized in the middle because physics says it has to be, and this becomes a very, very good basic antenna. So this is this is basically the basic antenna in radio that everything else is based off of. And because it's a half wave dipole, how long is it?
Half
half of a wave. Okay, so if your wave is 100 meters long, how long is the antenna? How long is that half wave dipole?
50.
50 meters.
50 meters. If the wave is 1 meter long, how long is the antenna?
19 inches.
No, yep, half of a meter, right? Which is about 19 inches. So really what this means is that we now have a fundamental antenna, which we can cut to different lengths, just like, just like an organ pipe that resonates on different frequencies and obeys the laws of physics. So this is a fundamental antenna. It's, again, the most basic antenna that there is for anybody to make or to design. And a lot of most designs come down to this as a basis. So we have a half wave antenna with this feed point in the center. Okay, now if we were to look at this antenna, this transmits energy perpendicular to the wire. So that would be straight up and straight down and out of the page and into the page, basically forming something the shape of a donut around the wire. So because it forms something in the shape of a donut around the wire, how much goes this way along the axis of the wire? If you look at, if you look through the hole of a donut, how much of the donut is in the hole?
Very little.
None.
Yeah, there's basically nothing, which basically means that a half wave dipole antenna makes a pattern that has no energy, virtually no energy emitted along the line of the wire. This is known as a broadside antenna because the energy is transmitted perpendicular to the antenna, or broadside.
Is that technically a torus?
It is. The shape that it makes is actually a torus. And it peaks at its center. It peaks perpendicular and then it goes down as you go around, and that actually forms a torus. Okay, so now we can actually make antennas. So the first thing we're going to do, according to the book, we're on page 33, by the way. Approximate length in inches of a half wavelength 6-meter antenna. So this is your first foray into actually making an antenna. So we're going to pick a 6-meter antenna. So now what we're going to do is go back to the frequency spectrum chart that we have. This right here. Did I close it? Oh, darn it. Let's see if I still have it. Nope, there's an azimuthal map. That means I probably closed it. Okay. It means I really need to open it again. Give me a second, everybody. US band plan update. Okay. So you might recognize this one. We're going to share this screen right here. Okay. So we're going to make an antenna for the 6-meter band. So because it operates from 50 to 54 megahertz, somebody pick a frequency to start with.
52.
We'll go with 52 because it's right in the middle and hopefully it'll get us some ability to go either direction. Okay, so we're going to go with 52 megahertz. This is the first time we're actually doing this for real. Here we go. What's the circle that I make to figure out what the actual wavelengths are? 300. What do I fill in there?
Divided by 52.
Right. Well, if I make the circle 300 F and
Megahertz
lambda.
and lambda.
300. Be able to make this circle because this is the relationship between the two. So since I don't know the wavelength is equal to 300 divided by 52. Okay, so I go to my calculator. 300 divided by 52, I get 5.76 meters.
What was the 300? Sorry.
Speed of light,
Oh,
because we're going back to the speed of light. Okay, so our wavelength, because this is in megahertz and this is in meters, our wavelength is now 5.76 meters. but that is a full wavelength, and we are making a half wave antenna. So what would a half wave be?
Oh, half of
Fi-
that, which is like
5.76 divided by 2, which would
Small
be 2.88 meters. Okay, so far so good. Divided by 2, we get 2.88. Okay, now we're going to take this and multiply this by 39.36 inches, because there's 39.36 inches per meter. That's how long a meter is. And we
Why are you
get,
going to inches at all?
because most people in the United States don't have a meter stick. Honestly, that's why.
39.36 inches
Yep,
equals
1
a
meter.
meter.
1
Yep.
meter.
And I get roughly 113.5 inches. But if I were to make this antenna, I would find that it was physically too big.
Way too long.
The reason
Way too
being
long.
that when you actually start making antennas, you will find that you have to take whatever length you get and take 95% of it. You actually have to shorten it slightly. And that's because wire has inductance, and it actually has a little bit of capacitance with respect to the ground. And there's some capacitance at the end of the wire. And basically it's real world effects. So you have this factor, which is 95%, which is real world effects. So we're going to multiply by 0.95 and we get roughly 108 inches. Now the book says 112 inches. Any guess as to what 112 inches would have come from? Remember, what frequency did we pick?
52.
52. Well, if I had chosen 50, that would be 2 out of 50, which is 4% difference. What is the difference between 108 and 112 inches? About 4%. So basically the answer that they have, the answer that's on the test is 112 inches. That's why it's 112 inches, because clearly they started with 50 megahertz instead of 52.
Wouldn't it be 4% longer? Wouldn't they be basing it off 56?
Take a look at the band. What are the limits on the band?
50 and 54.
54.
50 to 54. So they started at 50. And if we go through the math, we would find that if we start at 50 megahertz,
Yeah,
300 F lambda, 300 divided by 50 is exactly 6 times 1/2, because it's a half wave, is 3 meters. 3 times 39.36 is almost exactly 112 inches. And that's where they got that number.
Question, why is the antenna impractical if it's only 9 or 10 feet long?
Why is it what?
I thought we had said that this type of antenna would ultimately be impractical, but it's only about 9 or 10 feet long, yes?
Well, it depends on the frequency you're making it for. For this band, it's very practical. Let's say that instead, okay, here we go. We're going to pick a frequency of 1.8 megahertz. All right, somebody with a calculator, we're gonna round this up to 2 megahertz, which is at the very upper end of the 160 meter band. All right, here we go. What's that circle look like again? Somebody tell me. 300.
300. F
Yep,
lambda.
F and
Frequency,
lambda.
I lambda.
Yep, 300 and F and lambda. Okay, so we don't know our wavelength. So our lambda is 300 divided by F, which is 300 divided by 2, which is 150 meters long. Okay, so now it's a half wave. What's a half of 150 meters?
75.
75 meters times, we'll just go with 3.3 feet. I don't need to know inches. I just want to know how many feet. So that's 225 and 22 is 247 feet. And then we're going to multiply that by 0.95 to shorten it a little bit.
Okay, so I'm buying acreage.
Well, if you're doing 160, yeah. That's why 160 is a very challenging band to work on. That's exactly right.
Do people do that with like horizontal antennas?
They do. You can also put up a vertical at 1.8 megahertz. Okay, so let's go 1.8. What's 300 divided by 1.8? I get
Pretty
160.
tall.
I get 166.7 meters. Divided by, well, we're going to use a quarter wave here because I'll show you why in a minute. So we're going to divide by 4. Okay. 41.6, 41.7 meters times 0.95. 95% is 39.6 meters times 3.3 is 130 feet long. Okay, so that would mean that if I were to make a vertical antenna, it would have to be 130 feet tall. So the next time you're out driving around and you see an AM radio tower, you will notice a very tall tower. The reason being that that's a quarter wave vertical. Now, the tricky thing with a quarter wave vertical is what did we draw when we drew our wave? We drew our whole wave, right? What were the corresponding factors with a quarter wave, with a half wave antenna? What do the currents at the ends have to be?
0.
0. Okay, how about this antenna? What does the current up here have to be?
Oh, max?
I hope it's still 0. There's nowhere for it to go,
Well, okay.
right? Well, it's at the
Transmitted
end.
along the length of the antenna.
Right. It's so basically, if I start drawing my wave, I'm never even going to make it to the point where it goes all the way down. It's just going to be a quarter wave long, which is going to be this long. Like my pattern is going to look like this. So I'm going to have current maximized at the bottom, which is actually pretty good because I want to run my feed line in at the bottom. That's actually helpful. My voltage is going to be close to 0 at the bottom. But where's the rest of the antenna? Where's the rest of the antenna?
Coiled wire?
Part of it's missing. Where is it?
Ground plane.
Ground plane. So what actually exists is that there is a reflective surface, which I'm going to draw, which is the missing, which represents the missing other half of the antenna. So this quarter wave antenna has to have a ground plane. Essentially, it needs an electrically reflective surface so that, let's say that I am far, far away. I'm going to make myself far, far away. All right. I'm going to make myself far, far away from this antenna. Way over here. And I'm looking at this antenna. All right. How many ends of the antenna do I see where there's no ground? If I didn't know that there was a ground plane there, I just saw an antenna right there, I would see an end with no current, and I see a center point with peak, and down here, what would I see? If I didn't know that was a reflective surface.
It would have to be 0.
Well, I'd see another end of the antenna, wouldn't I? If I didn't know that there was a mirror there, and I can demonstrate this by taking a reflective surface and doing this. If I tilt this just right, you see, there we go. How many lights do you see in that image that I'm putting out there?
2.
There's 2, right? What if you didn't know that this was actually a piece of glass down below that's reflecting a light? Would you know there was only one light? The answer is no, you wouldn't. So if you have an electrically reflective surface, basically what it does is it creates the image of there being another half of the antenna somewhere else. And then everything is hunky-dory. It makes the world okay. It basically acts like a dipole. The one big difference is that the current that matches it is actually flowing down here in the metallic area. And this is exactly why you can build, for instance, on the roof of your car, an antenna that looks like this with a magnet in it. And this is a quarter wave long. Where's the rest of the antenna?
Car.
The
Top
roof
of the
of the
roof.
car. And what happens is that there is an electrode in the bottom of this antenna mount that capacitively couples to the roof of the car. And why does that work? Because we are talking about very high frequency AC. And what does a capacitor look like with AC?
Short or
It
short.
looks like a short circuit. So basically that flows current into the roof of the car, and the roof of the car mimics the other half of the antenna, which is also why if you have a fiberglass car, a fiberglass roofed car, it doesn't work. So the other cool thing is that if you take this antenna and you just make a quarter wave like this. Now, how many people would believe me if I said that this was a quarter wave length long? We're going to talk about this right now.
Yeah.
See this little antenna on my radio? It's only 7 inches long. So we're going to do the math right now and say that this is 146 megahertz. All right. Let's do the math. Somebody tell me what that circle says again. 300. Notice I'm pushing you guys to tell me. What does that circle have to say?
It's in lambda.
F
Lambda.
and lambda.
F.
That's right. Okay. We have a frequency of 146. We're going to cross this out. Lambda is 300 divided by 146, which is about equal to 2. So that is the 2-meter band. What do you know? How convenient. Okay, so now we're going to take a quarter wave. We're going to take a quarter of that. So that's about 0.5 meters. And take 95%. And it's like 0.48 meters long, which is about 19 inches long. Okay, now what I'm going to do is hold this up, and I want everybody to tell me if this antenna, first of all, is 19 inches long.
No,
It is not. Okay, how long is this antenna? This is about 7 inches. Okay, but what if I were to tell you that actually that antenna really is 19 inches long? Where is it 19 inches long?
It must be coiled up.
It's coiled up in the bottom. And then there's a straight section. So that electrically it's 19 inches of wire, but it physically only takes up 7 inches of space. So my question to you is, what do we remember
I have a
about?
question about that.
Yes.
So, there's an old law that wire, when it's coiled like that, is magnetized. How is this not different? How does
It is.
it is?
It
Okay,
is.
so if
Can't
it's
change the laws of
magnetized,
physics.
if it's magnetized tight like that, does it interfere with the frequency it's trying to produce?
It doesn't, it changes its impedance somewhat. The physical length, yeah, it'll change it a little bit too. So it's going to be approximately 19 inches. But more importantly, what's going to happen is a straight wire, as current flows, it's going to generate an electric field, and it's also going to generate a magnetic field,
Right,
right? So what's going to happen to that electric and magnetic field in that really coily part?
greater,
Hmm?
greater.
It should get greater, like a greater.
Except that it doesn't. You end up with cancellation because
Oh,
as
gotcha,
the
okay.
coil goes around, the magnetic field cancels on itself.
Gotcha. Okay.
So what you end up with is is greatly reduced efficiency. So why is that okay? So let us say that compared to a 19-inch piece of wire versus a coiled up piece of wire that's only 7 inches tall, your gain is compared to this is our reference, is minus 3 dB. That's the overall effectiveness of that new antenna.
But
Well,
it's still better than carrying around a super long antenna in your pocket.
it might be. Now, if let's say that you are transmitting and your signal is right on the hairy edge of being heard. So let's say we actually, and this is where we start to get into systems and understanding why decibels are important. So let's say that here's me standing out in the field somewhere, and here's a repeater over here with an antenna transmitting in all directions. And I have, let's say 1 watt, and at the receiver, the receiver itself has a sensitivity of minus 120 dB compared to that watt. In other words, 1/1,000,000th of a watt is enough to be there. But because of dispersion and of the signal, and because of things that I'm going through, I have a path loss of minus 122 dB. Okay, so I start with 0 dB, and then I have a minus 122, which is lower than that minus 120 threshold. Will I be heard? Yes or no? I will not. But how about if I came over here and I used the same radio, and my path loss, because I was a lot closer, is minus 114? Will I be heard? Yes or no?
Yes.
I will. So in other words, even with that crappy antenna, because I'm at a better spot, literally at a better place, this person gets heard and the one further away doesn't. So because notice that this minus 122 is only 2 dB less than that threshold, what would I possibly want to do with my antenna?
Alter the direction slightly.
Well, what the easiest thing to do would be
Point
to
it.
replace that antenna with the 19-inch stretched out antenna. And then instead of having 0 dB, my improvement is now 3 dB. I have plus 3 minus 122. My resultant is minus 119. And minus 119 is a little higher than minus 120. So that becomes the difference between getting heard and not getting heard. So if you're in a place where you have excess, you have gain to spare because of the path loss, you can get away with it. If you're in a place where you don't have gain to spare, you can't. This is actually called antenna loading, and it's very popular because you can make a long antenna very, very short. Okay.
Do you
So
mean you make a short antenna very long, or did you mean?
no, you make a long
Okay,
antenna
long
very
antenna.
short by coiling it up.
Oh, okay, okay.
So
So what you're saying, Scott, is that you could have the exact same length antenna.
mhm.
It's just in this diagram here where you're at the further away spot. If it's coiled up, you've got that impedance and that causes you to not be heard. But if you had the straight antenna at the exact same location and it's still 19 inches,
Mhm.
then you don't have the impedance with the straight antenna and you can be heard.
Well, it's really about the loss. It's about antenna gain and loss and efficiency because of how it's put together. By virtue of taking that and coiling it up, you have killed its efficiency. But maybe that's okay. You know, it's entirely possible. Like I've actually seen there's an antenna that's for sale that's called, like, I think it's called a stubby duck, and it's only 2 inches long. And it's still a 50 ohm impedance antenna, which means your radio's happy. And the whole thing is 19 inches of wire coiled up in a 2-inch thing. It's only 2 inches tall, right? That's really convenient, but its gain actually might be minus 10 dB. But if you're operating right underneath the repeater, who cares? You're still going to get heard. But I wouldn't, you wouldn't be able to use it at any kind of distance. So that becomes a compromise. See, that's why antennas are so much fun. Okay, a beam antenna.
On the wavelengths,
Mhm.
you said a quarter wave, a half wave. Is there any advantage to having a full wave antenna? If you had unlimited space and money,
Actually,
it
a
better
full
to
wave
have
antenna. So a full wave antenna that looks like that, if it's a full wavelength long, well, honestly, you'd basically probably want to feed it off center, which you can. If you feed it in the center, you're feeding it at a very high impedance point, so it's hard to put power into. You can actually, a half wave antenna is typically going to get you the nicest pattern. You can actually make an antenna that looks like this, multiple wavelengths long. What ends up happening is that, let's say you're feeding it right here, the different sections, if you go through modeling, will actually, like the way you would figure out what an antenna pattern looks like is that you would just pick a random point in space and look at little pieces of current and see what kind of energy, electromagnetic fields they generate, and then add them all together. And then you move this over to here and here and here and here and go all the way around in a 360-degree pattern at different distances and different angles. And what you would end up with is an antenna that the pattern might look like this, which can be good, except that in a lot of cases, what you lose is directionality. It works fine, but it doesn't necessarily have any higher gain. So we're actually going to talk about gain right now. Remember, what units do you think gain is measured in, everybody?
Decibel.
dB. Yeah, here's dB again. Okay, so a beam antenna is an antenna that concentrates a signal in one particular direction. So we can draw a couple of different ones. One is called a quad. So this is actually a full wave loop right here. So this is actually a quarter wave on a side, and this is called a loop. This is a full wave loop. A quad is actually two full wave loops, where one of them is driven energy, and the other one is parasitic, as it's called. And so this is actually, in this case, we'll call this the director. And then you have typically another one over here, which is slightly bigger. And this is actually, this is a reflector. So you have one driven element, which gets all the energy. What happens is, because this one is slightly bigger and spaced out, it catches energy and actually redirects it in the forward direction. The director radiates along with it and concentrates the energy in the forward direction. And this is known as a quad. If we were to instead use a dipole, and how long would a dipole be, everybody, in wavelengths? Half wave. And we actually had one that was slightly longer and slightly shorter, like that, and put them on a common boom, we would have the same kind of thing happening. We'd have energy going this way, and this one would be a parasitic element that would go this way. This is known as the reflector, and this is the director. And we would have more energy going forward. So that concentrates energy in the forward direction. And our radiation pattern, instead of being a donut, would now look something like this. The same thing here. So we would have more energy going in the forward direction. So again, this is called a quad, and this is called a Yagi, named after one of the engineers who came up with it. Now, here's another one. Everyone's familiar with this kind of antenna. What's that called?
That's a dish.
That's a dish. That's also a beam antenna. That's also a directional antenna.
Aren't these all beam antennas?
Well, actually, these guys are beam antennas, and the dish is a dish. But they're all directional antennas. They all concentrate the energy in the forward direction.
Wait, did you say the quad and the Yagi are both beam?
They're both beam
Dish.
antennas. Yeah,
Dish is something else. Okay,
the dish is a dish.
okay.
But basically what's important to note is that they're all directional antennas. And
All
they all have
directional.
something called gain. And what is their gain measured in?
dB.
dB. Okay. Now there's something else that there's a very special antenna called an isotropic radiator, which is a dot in space, which radiates energy in all directions equally well. This is called an isotropic radiator. You don't need to know that word, but it does come into play. At some point, you will actually see this. An isotropic radiator does not exist. It is a theoretical antenna that transmits equally in every direction. Again, it does not exist in nature, but it's used as something that if you were to draw its radiation pattern, it would basically be a sphere equally strong in all directions, which is why it's used as a reference. So because it doesn't physically exist, we now have something called a dipole. We sometimes use this as a reference antenna, which actually does exist. Well, it turns out that a dipole is 2.05 decibels better in its peak radiating direction than an isotropic radiator, which again doesn't exist. So there are a couple of different ways of comparing antennas. There's something called dBi, which is decibel gain compared to an isotropic, which again is imaginary. And then there's also something called this, right? So let's say this is a beam antenna. We're going to make an 8-element beam antenna. And we might say this has 12 dBd. That D means that it is 12 decibels better than a dipole. If we were to give it a dBi rating, it would actually be 14.05 dBi, because there's the I, and the dipole is already 2.05 dB better than the isotropic radiator. So when you go to get an antenna, it is very important to note the difference between whether they're giving you a rating in dBd or dBi, because one of them is going to actually be 2 units bigger than the other. And if they say 6 dBd versus 6 dBi, 6 dBd is a better antenna, because the I means that it's already about 2 dB weaker in the first place. Okay, so this coily antenna that we have that looks like this is known as a rubber duck. And the reason that it's a rubber duck is because it's flexible and bendable, and it won't jab you in the armpit. The disadvantage of doing this is that it does not transmit as effectively. You lose efficiency. Let's say you have your handheld radio. You decide to put it on a tabletop. Will that work as well as if the handheld radio is in your hand?
No,
Because
You-
why?
you lose your ground.
You lose your ground. That was perfect. That's exactly right. Basically, I am the other half of the antenna when I'm holding it. And what happens is that it's actually capacitively coupling to me. I am the other half of the antenna, which is also why I don't like operating particularly high power. It's not going to hurt you, but you know, if you're operating an antenna like that, I don't particularly want that much RF current going through me. A 5/8 wave antenna is, well, if we were to draw that, it would look like this. Here's the current. The reason that you would use a 5/8 wave antenna is that it has a lower
that light back
angle.
off?
It has a lower angle of radiation than a quarter wave. but a
I
2
figured
meter
that's why
5/8
you change your
wave,
computer screen. I said, I figured that's why you change your computer.
a 2 meter quarter wave, a 2 meter 5/8 wave antenna is about 41 inches long compared to 19 inches. Actually, I think it's about 45 inches long compared to 19 inches. So why would you choose one over the other? 5/8 wave gets out better if you're out in the middle of nowhere. 19 inches, that doesn't smack against your garage when you pull in. I can actually pull into, I can go to drive-in, drive-throughs. I can pull into a parking garage. I don't have to take the antenna off. Whereas if I had the bigger one, it would constantly keep hitting things.
What did you
So-
say about the lower angle? It has a lower angle.
It has a
what?
lower angle of radiation. And
Oh.
where are most of the people you want to talk to if you're in your car? Are they way up in the air or are they along the ground?
Mhm.
They're on the ground. So a lower angle of radiation is typically better for mobile operating. And finally, what's the disadvantage of using your handheld radio inside your car with the antenna inside the car?
It's absorbing some of the radio energy.
Yeah, basically your car is a big metal box. And that's why it does not work very well. That's why we put outside antennas, even going so far as to take a piece of cable and slam it in the door, because it still works better than using the antenna inside the car unless it's jammed up against the window. And even then you have to watch out because some windows are metallized and they actually will act as an RF shield. All right, everybody ready for a 5-minute break?
Sure.
I heard a question.
And
Somebody
a stiff drink. Just kidding.
I've got my coffee.
There you
10 in the
go.
morning. We used to be a sailor.
That just means the coffee cup never gets washed.
Yeah, exactly. I had a coworker recently who he never washed his coffee mug.
What?
He said that all of the built up stuff gave it better flavor. So this,
That is disgusting.
Peter, that's kind of unsanitary, isn't it? It's like, every time you put hot stuff in it, it sterilizes it. Like, I'm not so sure, but okay.
Clean a native man's coffee and they will never talk to you again.
Oh, no, my son makes me espresso. He just made me some Cuban coffee right now.
Oh,
Yum.
yes. good
Actually, we just
here's
got
what they were
we
talking
just got
about.
an espresso machine last week, and I made some last night for this. So,
Age Sumatran. Amen.
all right, I got to go run and use.
My husband is of the No Wash It brand.
Gives it flavor over the years.
I know a guy who does that too. He says his coffee cup is seasoned.
That is the word for it. Blue water seasoned.
And that was my coffee cup. I said, that was mine. Yeah, that was my coffee cup.
Just don't use soap.
Sacrilege.
Yeah.
Just remember, Navy is a 4-letter word.
You guys also sip us around. I'm a retired Marine.
Semper Fi, Bulldog.
Have you
got
gone
the bug
to
juice?
the Band of Brothers meetings?
I'm prior Air Force. I love to see all the Air Force guys in here.
Airedales, squids, grunts, brown dogs.
You may be Air Force, but I see you didn't leave the chair.
Exactly.
Drone pilot.
War planner.
All the Navy guys in here cleaning their coffee cups with bug juice.
Oh no.
Battery acid.
You had batteries?
Only if you're a shark. The subboys, whenever one went by, we'd call them sharks. Fly over Air Force bases, drop our tail hooks to show we were proud.
Has everybody been doing good on the pre-test? So far, I've been reading the materials, and with the class, I was getting low 80s, and now I'm getting high 80s, low 90s on all my pre-tests.
Yeah, taking those tests makes a difference repeatedly. It really does. You even get used to the format after a while.
And they're required to use those questions on the test. Like if you can nail the pre-test thing, like you're gonna pass it. Like when I started taking those tests before I started the class, and I was in the 50s, and I've just like worked my way up. Like I'm in the high 80s, low 90s now.
Are
Anybody
any
else
of you?
thinking about doing the general test also?
I was just about to ask that. I'm wanting to do it. My wife told me it's best to do it while it's fresh in your head. And the same day she told me that, one of the guys here is a hams. He's a extra amateur, and he was like, Ramon, his name's Red. He was like, Ramon, as soon as you finish the technical exam, the technician exam, go straight to the general, because some of the questions in the general are in the technical, and your brain will already have that memorized and fresh. So it's best to jump right on into the general. I actually emailed Scott to ask him if he was running a general course or if he had the material that we can study with.
Well, you know, here's the thing about the general exam. There's the big differences you'll see is if you look at this right here, the frequency allocations that are available to the general are essentially they add HF. And what you have to know is you have to know your frequencies, your band edges, you have to know, excuse me, power limits, and you have to know like maximum bit rates and things like that. And there's a little more technical stuff on antennas.
I started taking some of the practice tests for the general last night, and like, boy, it seemed way harder.
It is, but I mean, you know, there's again, it's a little more math, but the one thing that doesn't change, the basic rules, which we haven't gotten to yet, are the same. And you can be a volunteer examiner for technician license exams. You have to know that. And yeah, I mean, it's, you know, and for instance, there's more Morse, you're right, you have more opportunity to use Morse code. So you have to know more about the modulation techniques.
Scott, a question about the exam on Friday.
Mm-hmm.
I understand they watch us very, very closely.
Yep, we do.
I'm allowed to have a piece, right? I'm allowed to have a piece of paper.
Yes.
At the beginning, it has to be blank, but am I allowed during the test to actually write down the formulas as a reference and keep them in front of me?
Yep.
Okay, and also, okay, but I have to wait until the test starts for that to occur.
Yep.
Okay, and if I even so much as look away from the monitor, I'm just
well, no, because we have a second monitor. I mean, basically, because we're listening, we have audio also. So, and the thing is, we've also at the beginning of right before the beginning of the exam, we ask you to take the second camera and do a scan of the room, up, down, and all sides, to make sure there's basically nothing to look at.
Oh, okay.
Scott, there's a hams operator here named Red. He's a VE, and he's told me to tell you that if you guys require an additional VE, he'll be here. He can proctor my exam, or he can help anybody in this area because he's free.
Yep. Up until about a year ago, there was a requirement of a proctor, and the second camera did away with the need for a proctor. So
yes, that was from COVID.
Yeah, I mean, that was really a big driver of all that. The fact that, you know, it made it difficult. But all right, everybody ready to go again?
Yeah.
Okay, we are on page 36. We are on page 36, which is feed lines and connectors. Okay, so now that we have antennas, we have to be able to get power into them, which means we have to be able to deliver power to our antenna. Okay, So feed line, the most common feed line is coaxial cable. This is what we use for cable TV. This is what most people use for ham radio as well. The reason we use coaxial cable is because it can be built such that all of the signal is contained inside. So if you do it right, it doesn't leak RF anywhere. You have a center conductor and you have a shield. This is typically filled with some kind of dielectric, like a polyethylene plastic. It can also be filled with air, basically to keep the center conductor separated from the shield. The outside is usually an ultraviolet proof jacket, typically waterproof as well. So you can take the whole thing, leave it outside. It doesn't degrade in the sun, and you could bury it. It doesn't degrade in underground. Very easy to use, relatively cheap, and works really well. So that's coaxial cable. One interesting thing about coaxial cable is that if we look at it from the end, it looks like this. So you have the center conductor, and then you have the shield. One thing that's important to note about this is that the density of current, because they have to be equal and opposite on the center conductor, clearly is not the same as it is on the shield. And in fact, the spacing that you have in between there and there forms a capacitor, because it's two pieces of what it's basically two electrical plates. In addition to that, you also have along the length of the wire, you have an inductor, because every wire has some inductance. So what that means is you have something that looks like this. Actually, let's do it the other way. Something that basically looks like this. I still did that wrong. It's early. Give myself a break. Otherwise, it would be shorter. Basically, you have a whole bunch of like an infinite string of capacitors and inductors. So now the question that I would have is, if you look at this, how much power is actually killed by going through those inductors and capacitors? And the answer is virtually none. So coaxial cable, if it doesn't have any resistive losses, is actually very, very good. It doesn't effectively kill anything. But now let's say that this actually ends in an antenna, which we're going to put a big letter Z because it has impedance. Well, okay, that's now in series with a capacitor, which is now in parallel with an inductor, in series with a capacitor, in parallel with an inductor, in series, in parallel. That basically means that what you end up with is, if this is a certain impedance Z, you also have a characteristic impedance of the cable. Now, most cable that we use has a characteristic impedance of 50 ohms. What that means is that if you have a 50 ohm load, which is what's using your power, and you have a characteristic impedance of 50 ohms in your cable, that means that looking into the cable from the other end, no matter how long it is, that's kind of the definition of characteristic. It's a characteristic of the cable. It will have, you will see a 50 ohm impedance. If your radio is designed so that you have a transistor amplifier that has an output impedance of 50 ohms, you have a perfect match. You have an impedance match. So you might remember yesterday I mentioned something called an impedance matching network. Impedance matching network that we looked at looks like this. Does everybody remember that?
Yep.
Okay, that's an impedance matching network. What that does is it basically would go right in here and allow you to tune the capacitors and inductors so that the impedance, whatever it was, from here to the outside world would be matched to what your radio was looking for, and allow you to basically allow you to believe that you're looking into a 50 ohm impedance into the real world, and that the power coming down from the antenna through the feed line is matched properly to your antenna, to your radio. And it allows basically bidirectional maximization of power transfer. And that's why we use impedance matching networks. Okay, impedance is measure of opposition to AC current flow in a circuit. We covered that. It's also measured in ohms. Most coaxial cable is 50 ohms when we use it in radio, and that's because most radios have a 50 ohm impedance. Okay, so now what we're going to say is, are all cables created equally? And the reason that I'm going to ask that is because we're going to look at some different coaxial cables. All right, so these are all 50 ohm cables. Now, what makes a cable 50 ohms versus 75 ohms, if I were to draw it from the end, is the ratio or ratios of diameter of the center conductor to how far apart they are. And also we can also have the material inside that changes the dielectric constant a little bit. So essentially what we have is a combination of things which we can scale up if we want to, or we can scale down. So long as the ratios are the same, the characteristic impedance does not change, because it's based on the ratios of the geometry. So you can have something like an RG 174, or you can have an RG 8, or you can have a 3-inch hardline, which is actually rigid cable with 3-inch diameter. So long as the proportions are the same, they will all have a characteristic impedance of 50 ohms. If you change those numbers slightly and you keep them the same, maybe the impedance goes up to 75 ohms. Doesn't really matter. So long as the ratios are consistent, it'll have the same characteristic impedance. So now I will ask you the next question. Why would you pick one over the other? And this is just for everybody. Why would you pick one cable over a different one?
Better
Let's hear some
reception of the
answers.
bands.
What?
Better reception of the bands.
Inherently not really.
Convenience.
Convenience,
Cost.
yeah. This
Cost.
3-inch cable, it's really heavy and it's really hard to use.
Right.
So that's one.
Price.
Price, that's right. The really big stuff is really expensive. The really little stuff is really cheap. How about another one?
Signal loss.
Signal loss. And why signal loss?
Well, if you got a long line, you don't want a lot of signal loss.
Right. But what makes it have signal loss?
Resistance.
Resistance. That's right. And which wire is going to have a higher resistance?
Thicker,
Internally?
larger wire.
Higher resistance?
Smaller.
Smaller wire. That's right. So this cable is actually going to have high loss. This one is going to have very low loss. And on top of that, what you'll find is that there's something called the skin effect. The skin effect is the fact that on a given conductor at RF frequencies, depending on the frequency you're using, the higher the frequency, the more the current flows right on the surface of the wire. At DC, it flows uniformly throughout. At AC, it flows closer and closer to the surface, which basically means the higher the frequency you go, the more the current, the more the electrons flow almost completely on the surface. And what that ends up doing is it also means that as the characteristics of your cable change size-wise, your losses go up as your frequency goes up. And now what I've pulled up, notice this chart that says coax loss per 100 feet. I'm actually going to pull up a different one. Here we go. Okay, so RG 174, that's the really little stuff. Notice that, let's pick just at like 400 megahertz. That's very close to the 70 centimeter band. So per meter, which is about 3 feet for RG 174, your loss is 0.6 meters, or sorry, 0.6 decibels per meter. So let's say you have 50 meters of cable, 0.6 times 50, that would be 30 decibels. That basically means that your signal is cut down by a factor of 1,000. Essentially, if you have 1 watt coming in one end, you'll get 1,000th of a watt coming out the other end. Where does the other 0.999 watts go?
Heat.
Turns into heat. Losses in cable turn into heat. Okay, so now that might still be okay. But now let's crank that up to 1,000 watts. If you have 30 decibels of loss, that means that your 1,000 watts will produce 1 watt coming out of the other end.
Ooh,
Where does the other 999 watts go?
cooks your cable.
Yeah, your cable's already really tiny, and now it's just turned into a 1,000-watt heater, right? Which will probably destroy the cable. So there's a power handling capacity that's associated with cables as well. All right, so now let's go down to RG58. Notice our red line at 400 megahertz is about 0.4 of a decibel per meter. So that 30 meters that we started with, no, 50 meters that we started with, now it's 20 dB. Okay. So now we're down to 1/100th. So that's a little bit better, right? One watt in produces 100th of a watt out. That's still not good. So let's go down. Let's just skip the 8X because we're just going to ignore that one. Let's go down to the purple line, which is our 9913, which is a really, really high quality cable. 0.1 decibels per meter. So we're going to multiply that by our 50 and we get 5 dB.
5 dB.
Okay. So if we think back, what is 3 dB? Everybody, what is 3 decibels equal to? How many times?
2.
That's right. So 5 dB is pretty close to 3 and 3 because that would be 6. So it would be a fairly good estimate to say that we're now at, okay, let's say 6 dB. So the first 3 dB would cut our power in half. The second would cut our power in half again. So now we're at 1/4. Well, just by switching cable, now our 100 watts or our 1 watt in is producing 1/4 watt out. Well, that's a heck of a lot better than 1,000th, right? And it's a heck of a lot better than 100th. And it doesn't heat up as much. And that's why it's important to choose the right cable for the right frequency that you're using. Now, if you're running a television or a radio station and you're pumping out 25,000 watts of power or 100,000 watts, this cable will probably melt. You would obviously need something bigger, which is why even though the loss might be acceptable, it's still going to melt the cable. So you need bigger and bigger stuff to carry that amount of power. There are also charts out here for different kinds of cable. And notice for 9913, these are dB per 100 feet. So it's important to look at the lengths, decibels loss per something. But then once you know how long your cable run is, you'll find out if it's acceptable. So what happens if you're building a radio and internally you have a 6-inch jumper that you're using to move energy from one place to another, like one circuit board to another?
A jumper?
Yeah, a little jumper cable, like about that big, 6 inches long. And you look at the really tiny stuff, and at 440 megahertz, it's 17 decibels of loss, but per 100 feet. Let's say your cable that you're using is only 6 inches long.
Extremely low loss.
Yeah, extremely low loss. In other words, for that, you're probably okay to do it. So everything is you have to look at based on how you're using it. And that's the tricky thing with cable. That's why it's important to know that those cable losses go up as frequency goes up, and the losses also go up as your dimensions go down. So the smaller it is and the higher the frequency, the bigger the loss.
Do you have an example of where the heat is listed? So I could see what that looks like on a package to understand whether the heat loss would be,
Well,
something that would burn up the cable.
You just have to figure it. You just have to do I mean, for the most part, you just have to look at how much power would not be going out. Typically what you'll get is when you look at a piece of cable, it'll give you a power, like a power rating in watts. And that'll have all that figured into it.
And you
So,
just have to stay under the wattage of that power rating.
so for all intents and purposes, I mean, if you look at like RG8 is that's actually the next question. The electrical difference between RG8 and RG58. So if we were to look at RG8, let me pull this up. I'll get a picture of RG8 versus RG58. Let me see if there's a nice photo of it.
Tell us what RG means, RG8 versus RG58.
I believe it's just radio gauge. I don't remember exactly what it means.
Okay, I didn't know if there was some,
No,
anachronism.
it's just a standard naming convention. Here we go.
It was a military thing.
Yeah. So, okay, so notice RG, can everybody see that picture that says RG8CU? Let me pull that up. Here we go. Okay, so notice there's RG8, RG50, RG58, 59, 62, 6, and 11. RG8 is somewhere in size between 6 and 11. Notice what it looks like compared to RG58. So obviously it's going to be heavier. It's going to be a lot thicker. So you're going to have to manage it. You can't bend it as tightly. You probably can't slam it in your car door and still have the foam seal properly. RG58, you can get away with it and it still seals quite well. So your car doesn't leak when you slam it in the door. So RG8, again, is going to be something more like the 6 or 11, probably more like the 11. So because of that, it's physically bigger, so its loss is lower than the 58 would be at a given frequency.
Is the CU on that for copper?
The CU and the B, there's AU, BU, CU, and that's kind of a definition of what the shielding looks like. Some cables are going to be single shielded, some are going to be like braid plus braid plus an aluminum shield. There another thing that when you buy a piece of cable, it'll say 99% tinned braid or tinned copper or tinned shield. Another cable will say, 70% coverage, which basically means that 30% of that shield is empty space. Well, if 30% of the shield is empty space, is it as good a cable as the double braided stuff? You're actually going to have some signal that leaks out because it's not shielded as well. So when you buy a piece of cable, you have to look and see what it's actually rated for power wise and what the shield looks like. Which of the following? Okay, so we're on to page 37. The lowest loss at VHF and UHF, that would be air insulated hardline. Basically, it's a pain in the butt to work with, but air is a very good insulator, and it can be made into cables that are very, very large. So hardline, when I say hardline, that might be a little confusing to people. So I'm going to pull up something called Andrew Heliax. So this is a polyethylene insulated hardline. And notice that it's actually copper and copper. The shield is actually solid copper. This has a diameter, for instance, of 7/8 of an inch. As you can imagine, it's very, very, very heavy. And because that center is polyethylene, and notice how thick the center conductor is, right? Pain in the ass to work with. I mean, if you have a 200-foot spool of this, you need a truck to move it. And the coil is going to be 8 feet around. And notice it's also over $3 a foot. So
It's not so bad.
not so bad, I guess. Depends. If you own a TV or radio station, it's not so bad, right? If it's just you, I mean, you know, this could be, you know, 1,000-foot piece of cable just for the cable.
Did you
So-
say that the diameter would be like 8 feet around? I mean,
When you coiled it up to move it around,
you got
I
a
mean-
big, your coil.
yeah,
The thing you're moving is, okay.
could be 8 feet around. I mean, we actually, when I was in college, we bought 200 feet of 2-inch hardline for our repeater. The connectors alone were $300.
Wow.
And I mean, somebody basically gave us the cable for free, but we had to pay them to drive it down, and it took 4 people to carry it. And then we had to unroll it. You know, it
And
was,
these are cables, Scott, for UHF and VHF?
that was for a VHF repeater that we were doing. Because we wanted to minimize our signal loss.
What are cables laid under the ocean across
They're
the
big.
ocean called, or what are they like?
They're transit line. Mostly they're fiber optic now.
Say fiber, right?
Yeah, they're mostly fiber optic. But not originally. They used to be, you know, they used to be coaxial cable. Or they used to be single wires, and they would be parallel line. So not all cable has to be, not all cable transmission line has to be coaxial cable. You can also have transmission line that's just 2 parallel wires. And if you do this and put plastic around it and make it look like this is known as TV twin lead or just ladder line. And if anyone if anyone remembers having rabbit ears on their TV, that's what this is. That has an impedance of 300 ohms or maybe 450 ohms, depending on what you got. And it's just basically 2 wires in parallel in a plastic jacket. And that's known as ladder line or twin lead. Okay, the most common cause for failure of coaxial cable is moisture contamination. Why should the outer jacket be resistant to ultraviolet light? The reason being that ultraviolet light, if it's not resistant, will crack the jacket. Once the jacket cracks, you get water in it, and water is the cause of failure for cable. Air core coaxial cable compared to foam or solid, air can have water in it because you get moisture. And what happens when you get water condensing inside a cable? It corrodes the copper, and corroded copper is not a good conductor anymore. So you basically have to have water absorbing materials, either a desiccant, or you have to pump dry nitrogen into it, which also means it has to be pressurized, which is another pain. So that's why
would
air
coax
core,
be air-based?
why? Because air is a very good dielectric. And typically you just have like a little coil of polyethylene that's spiraled around inside. So yeah, air is actually a really good dielectric. But again, if you're going to do that, because it also keeps the weight down, you typically have to use pressurized nitrogen in it, which means it has to be pressure tested also.
When you say dielectric, do you mean just insulator?
Yep. That's exactly right. Okay, let's see. Next, we're getting to connectors. And I did bring this up. Oops, I didn't mean to do that. Okay, let's see. Coax connectors. Yep. Okay, coaxial cable connectors. Right here. Everybody see these different connectors?
Yes.
Okay, the one all the way on the right-hand side, that's called an SMA connector. That teeny little thing. Most radios today have an SMA connector on them. The one second from right up at top, that's called an F connector. That's something like you would see in your cable TV system.
Yeah.
Then as we go down, second from right, those are called UHF connectors. The one on the very bottom, let me see if I can. The one on the very bottom, second from right, that's called a PL259. The one slightly above it is an SO239. They're actually called UHF connectors because people weren't using UHF when they were created. So that became known as universal high frequency. So interestingly enough, a PL259 connector is a UHF connector, as it's called, but it's terrible for use at UHF frequencies.
Help, Mr. Wizard.
Yeah. So basically, this is actually really good for use at HF frequencies. The one on second from the right on the bottom. The one all the way on the left, these are, notice that they actually have like a center pin and then like a spring-loaded something and then what looks like a gasket. That's actually a waterproof connector called an N connector. And those are actually good for frequencies up to several gigahertz.
Oh,
Yeah, but they're also a lot more expensive and they're a lot harder to work with.
That was a question in the test, right? That
Yep.
it kept coming up in my practice test that
That's
that was
right.
400 megahertz or something.
Yep. And so basically the N connector is really, really good for high power levels and for UHF and above, all the way into the microwaves.
Cell phones.
Cell phones. Yeah, exactly. Yeah. If you deal with anything in the way of microwaves on you'll use those connectors on the left-hand side. Okay. Why should coaxial connectors exposed to the weather be sealed against water intrusion? To prevent an increase in feed line loss. Basically, if those connectors, which are the ends of your coaxial cable, are not watertight, you'll get water in your cable. And what does water do to your cable?
corrodes it.
That's right. If there's one thing you remember from all of that is that if you get a wet a cable with water inside it, it's not a very good cable anymore. A loose connection in an antenna or feed line can do all kinds of crazy stuff to your SWR reading. So it's interesting that they brought that question up before they actually introduced SWR. So we're on page 39. SWR is standing wave ratio. And what it is in gross terms is if I have a piece of transmission line that's going from my transmitter to my antenna, this is an antenna. Standing wave ratio is a ratio of how much power is going out to the antenna versus how much, when it got here, is being reflected back. So ideally, and in particular, it's a calculated number such that a perfect match, which means that nothing ever comes back, is actually known as 1-to-1. So a perfect SWR is
Nothing comes back or everything comes back?
Nothing comes back. In other words, I sent power out and I never see it again. 1-to-1 is a perfect match. You have no power coming back. And that is a 1-to-1 standing wave ratio. So you can actually get an idea of what this is. Let's say your feed line is 50 ohms and your antenna is 150 ohms. Well, clearly these are not the same. There's a mismatch up there. So what happens here, actually, you end up with a 3-to-1 SWR, which is not a particularly good match. Now, interestingly, you could also replace this. Instead of 150 ohms, you could replace this with 17 ohms, and you'd still have a 3-to-1 SWR. In other words, the ratio of your impedances is 3-to-1. And that gives you the same mismatch, whether it's 1-to-3 or 3-to-1. It's still a 3-to-1 mismatch. So a mismatch of 4-to-1 SWR, that is a mismatch. And if you have something like that, what will happen is that a lot of your power that's going out, let's say that you have 50 ohms here and 200 ohms here, you'll have some of your power going out and a lot of it coming back. When it gets back here, if there's nothing to turn it around backwards, it ends up being dissipated as heat in your transmitter. Well, what that does is that it heats up your transistors. Your transistors experience high voltages and they blow up. So what your transmitter will do at that point is that if it sees an impedance mismatch that's that bad, it will fold itself back. It'll actually employ something called fold back circuitry, which limits the amount of power going out so that it limits the amount of voltage that it sees coming back and protects itself against being destroyed.
I have a
Okay.
question.
Yeah.
I'm sorry, I think I missed a little bit. Why does the power go back?
Well, it has to go somewhere. So, I mean, let's say you have let's go back to and you can actually try this. Let's take a jump rope and tie it to a doorknob. And you whip the jump rope. What happens when it gets here? What happens to the energy?
It goes to it with the jump rope.
It actually will cause a reflected wave to come back, which will actually, if your hand is moving up and down, it will try to move your hand around back and forth. You should try it. Try it with a piece of rope, tie it to a door, and then whip it up and down and see what happens.
Okay.
The same thing happens when you have an impedance mismatch in a piece of cable, where it's connected to another piece of cable or to an antenna. Basically, what you'll end up with is a wave that is reflected back from the end, from that mismatch point.
Right.
And what ends up happening is that power has to go somewhere. And because there's a voltage associated with it, if you have voltage that's being driven into your antenna in the first place by your transistors, you'll end up with more voltage potentially coming back, which can destroy your circuitry.
Okay.
Okay, what happens to power that's lost in a feed line? What does it turn into?
Heat.
Heat, okay. And so why is it important to have low SWR?
Power goes
Don't beat
away.
up your components.
Yeah, it'll protect your components. It'll also, like, how much signal comes out if you have a bad mismatch up here?
Much reduced signal.
Much reduced signal, that's right. Okay, so if I'm going to have an external SWR meter, I would typically put it right here, because I want to know what's happening. What I want to know basically what the transmitter is seeing is happening in the outside world. So because I want to know what the transmitter is actually seeing, I want that meter as close to the transmitter as possible.
Is this why so many sets have the SWR calibration built in?
That's why so many radios have an SWR meter built in, because that's basically a representation of exactly what the transmitter is seeing. That's exactly right. I actually have an external meter and an internal meter, because I have my meter, I have my external meter built into an antenna tuner, which again looks like this.
For us beginning radio people, should we have that set up?
I think it's very important to have one, because what it allows you to do is really get an understanding of what's happening. Now, if you get a radio that has an internal antenna tuner built in, typically those will only tune an impedance mismatch of about 3-to-1.
I've seen a number of devices that appear to measure the elliptical pattern of the radio transmission in graphic form. Are those helpful?
If you're talking like if you're talking a VNA,
I think so.
a vector
I've seen
network
the devices
analyzer.
advertised that you can attach that would measure the output or the pattern of the wave.
Well, I mean, you can get a signal analyzer, but are you talking
Thank you.
something
That's what it is. Yes, that's it.
something that looks like this?
Yes.
Oh, that's a VNA. And typically that actually puts out its own signal. So you wouldn't use that. You would basically remove your transmitter if using a VNA or an antenna analyzer, and it would essentially put signals of different frequencies into the circuit, into the system, and it would give you a plot of what the system looks like at different frequencies. This is actually known as a Smith chart. This is on your extra class exam.
Mm.
And it has resistance circles and reactance curves. So that's kind of like the that's the advanced class.
Never mind.
Yep, but it's actually really useful to know. So if you want to get a VNA, I will never tell anybody to not get a VNA. Now, the other thing to get is an antenna tuner, or sorry, antenna analyzer, which replaces your transmitter for a little bit and allows you to see what's happening in your antenna. The reason that this works so nicely is because this device does not care what the SWR is, and it's actually allowed to transmit from 0 to, let's say, 460 megahertz continuously at a power of 1 milliwatt, and is sensitive enough to see what's going out and what's going back and plot that. Because it's only transmitting at 1 milliwatt, it's not a ham radio. It's a part 15 radio, which we're going to get to, which basically means it's an incidental transmitter. Its output power is so low that you don't have to worry about it being licensed, which means you can transmit on bands that aren't ham bands at all. So what it can do is it can give you a curve of what your SWR looks like from 0 up to, let's say, 500 megahertz, even in areas that aren't ham bands. So you can see, oh, okay, well, I have a dip here at 164 megahertz. So my antenna is too short for one band or too long for another. And normally I'd have to just guess because I couldn't see, I couldn't legally transmit a signal in that band. This thing allows me to actually check and see what's happening in that band that I have no privileges on. Okay, why do most solid state amateur radio transmitters reduce output power as SWR goes up? And that's to protect the output amplifier. There's also something called a directional watt meter. SWR is a calculation of forward and reverse power. Well, you can actually use something called a directional watt meter, which is a watt meter that typically has a slug or a device that you can either turn that way or that way, and it has a meter. And it says when it's pointed one way, what is my output power? And when it's pointed the other way, what's my output power? And I can use a calculation and figure out what that happens to be. Now, if I don't want to go to that point where I actually go and buy one of these, the most common one is called a Bird 43, which is kind of like a reference standard, and they've been made for years and years and years, and it looks like this. That's a reversible watt meter. Notice they're $400 something. You can very easily go and get, for instance, an N7JI 949E, which has, if I can get a nice picture of it. What I really want to see is that, and I want to zoom in on, come on, there we go. Why is my window there so small? Anyway. Okay, so as I hover over this, you'll see that there's actually really? It's not a very good zoom. There we go. Okay, there's the meter. And notice it says forward and reflected watts, and it has those little red lines. This is actually known as a cross needle meter. And what it does is it simultaneously measures forward and reflected power in watts. And it has those curves to indicate that anywhere where those two needles cross, that's what the standing wave ratio is based on the two values of forward and reflected power. So essentially, this is a very convenient way to see what your SWR is. Practically speaking, what you're really looking for is you see all the way on the right-hand side where reflected power goes to 0. You're basically looking to see that when you're transmitting, that reflected power is as close to 0 as possible. And notice all the way down on that bottom line, there's a number 1 on that red line. That's a perfect SWR of 1 to 1. So this is typically what I use. This is what a lot of people use for measuring their SWR instead of going through the calculations.
Got a question for you.
Yep.
Real world, using that item, that tool right there, what is a real world SWR? What is it commonly seen and accepted?
Well, I mean, when you say, in other words, what are you aiming for?
Well, I know what you're aiming for, but in the real world, ivory towers are what you want, but sometimes you get there.
If I get down to 1.5 to 1, I'm happy.
All right, that's what I wanted to know.
Yeah. 1.5 to 1, I'm still getting 85, 90% of my power out. And depending on the cable I'm using, I'm okay with it. I'd still like to see it 1 to 1, but sometimes your impedance is such that you can't get down that low. You try, but you can't do it.
Scott, I got a question.
Yeah.
I plan on using a handheld.
Yep.
What can you do to lower the SWR in a handheld when you're trying to communicate, or is there any way to enhance the frequency from a handheld? Or
You won't, I mean, typically you're not going to have a problem with it because you're not changing frequencies. You're just going to cut an antenna and it's going to work.
Most of that would just be off the shelf stuff that's already basically set up correctly.
Or if you buy like a VHF general VHF antenna, you would use an antenna analyzer, and you'd have like a stainless steel rod, and if the frequency is too low, you snip 1/8 of an inch off of it, and you see what the new frequency is. If it's still too low, you snip a 1/16 inch off, and then another 1/16, and then another 1/16 until it's right in the right spot.
So basically these SWR ratings are for when you're building your own radios.
Well, it's for when you're building your own antennas.
Yeah, that's what I meant, sorry.
Yeah. Or when you're using an antenna in a way that wasn't necessarily intended to be used.
But by and large, you're saying that if the radio says 50 dB and the antenna says 50 dB, you can pretty much
50 ohms?
trust it.
Yeah. I mean, if it's a 50 ohm, I mean, the radio is going to be 50 ohms. I mean, that's what everybody builds to. And if you buy 50 ohm cable and your antenna is a 50 ohm antenna, it should be a pretty good match. I mean, you can always check, but it's probably going to be fine.
It seems like in general, it's kind of like a sort of just a pay to play. Like if you just buy, like it seems like all the better stuff is more expensive. So it seems like you could just buy good stuff and it should all be good. Is that
could be? Could be. But the question is, are you always going to be buying something, or are you going to be using something in a way that you never intended to? So, and that way, I mean, you don't have to own every one of these pieces of test equipment, but it's important to know who has one. Because there's probably somebody around who has one. I mean, I have an antenna analyzer. I haven't bought a VNA, but I'm going to. I've got an oscilloscope. I've got I've got multiple different power watt meters and SWR meters. I can, like if somebody gives me a call and said, "Hey, I put up a new antenna. You want to come check it out for me?" I don't have a, I said, "Sure, I'll bring the analyzer." And
antennas you buy from the store are 50 ohms. So
right.
You can buy 50 ohm antennas, but depending on where you buy it, but where you put it, where you install it and what's around it, it may change.
Yeah. So let's say you buy a pre-cut half wave dipole, right? And you stick it up in the trees. Okay. You stick it between two trees and it's 10 feet off the ground. Or you stick it in the trees and it's 25 feet off the ground. Or you stick it in the trees and it's 40 feet off the ground. It's not going to be the same impedance. It's going to be coupling to the ground, right? If it's parallel to the tree, let's say you set it up vertically, it's going to be parallel to the tree. It's going to couple to the tree. If there's an RV park next door, it's going to couple to the RV next door. If you have a metal roof, it's going to couple to the metal roof. I mean, if you get a quarter wave mag mount antenna and stick it on the roof of your car, it'll be fine. But when you start dealing with other things, other combinations, you take that quarter wave antenna and you put it on your trunk lid. Well, it's now below the roof of your car, right? The roof of your car is now in the radiation pattern of the antenna, which means it's going to affect it. And you don't exactly know how it's going to affect it. You might have to go and trim it slightly to get it to be 50 ohms.
Are there devices that you can purchase that will change the standing wave ratio of an antenna you put up like between the trees, because you can't easily change the direction of the trees?
Yeah, I mean that's basically you can actually, okay. So remember we talked about transformers?
Yes.
Okay, so let me ask this question. If I build a transformer that looks like this, and I have n to 1, that's my turns ratio, right? Well, that changes my voltage. My voltage is proportional to n. My current is proportional to 1 divided by n. What is Ohm's law? Somebody give me Ohm's law again. E equals
I times R.
I times R. All right, E equals I times R. So R is equal to E divided by I. Okay, so now what do I know about my turns ratio? It's multiplied by N times V. And what do I know about my current? I divided by N. So I have V over I, which is my initial resistance times N squared. So what happens to my resistance if I push it through a transformer? What's that additional factor, everybody?
Resistance or impedance?
Yeah, but what is that? What's N squared? N is the ratio of the turns that I wrapped around the transformer. If I have 10 to 1, what's N squared?
100.
100. So if I have 3 ohms over here, what will I see on the other side? If I were to measure it, I would see 300 ohms. Trippy, right? It's an impedance matching device. A transformer can function as an impedance matcher. And that is why sometimes people will actually build a transformer that's a 9 to 1 match. Internally, it's a 3 to 1 turns ratio, which gives you a 9 to 1 match. So that will say if I have, for instance, 50 ohms over here, what will I have on this side? 450 ohms. The other thing I can do is I can say that I have a high impedance antenna, for instance, 2000 ohms, and I want 50 ohms. What would the ratio then have to be of my impedance? Be about 40 times? Everyone agree with that? So basically my ratio would actually have to be about 6.5 to 1, and it would be higher on this side. And that would be a way of feeding a high impedance antenna. I could also, and I've had this, I had a vertical antenna on my car, which had an impedance of about 3 ohms. And I wanted to feed that into 50 ohms. That's a factor of about 17 times. So that's about 4.2. So I'd have a turns ratio of 4.2 to 1. That is my impedance matching transformer.
And
that is on my car.
How does that affect, wouldn't that also increase or decrease the voltage?
Who cares? In other words, the radio doesn't care. And yes, that increases the voltage on that side, right? But who, or actually it increases the, yeah. So, but the question is, who cares? It actually decreases the voltage on this side and increases the current. But the antenna is
incidental for your purposes.
Yeah, the antenna is designed for it. So long as I build my transformer sturdy enough, it works fine. And that's used for impedance matching.
Are there off-the-shelf antenna transformers?
You can buy a 9-to-1 transformer. You can buy a 4-to-1 transformer.
I.e.,
Typically,
yes.
you typically won't get like a 1.2-to-1, but yeah. And very often they're matched with something called a balun. You can get a balun, which is a balanced line to unbalanced line, bal-un, with a 1-to-1 match or a 4-to-1 match or a 9-to-1 match. You can also get something called an un-un transformer, which is unbalanced with like coax, because it's not equal, to unbalanced, which is another piece of coax at a different ratio, like 1-to-1 or 4-to-1 or 9-to-1. Yeah,
And those are
lots of
just sort of like-
different options.
And those are sort of like ratios that would solve like a common mismatch problem.
Yep. Or like feeding an antenna that you know is like a folded dipole, which is a 300 ohm impedance, instead of a standard dipole, which is about 75 ohms. So, and that's why I have so much fun with antennas, because antennas are the one place where there's still black art, and you still have to really use your wits to figure out what you're going to do. Because sometimes I mean, I can't tell you how many times I've built an antenna that really should have worked and didn't work worth a crap. And I just end up cutting the whole thing apart and starting with something else, because it should have worked. The math works out, but it doesn't work. And it doesn't work because the real world does not always equal theory.
We'll stop inspiring so much confidence.
I know, but that's part of the fun, you know. But sometimes when you build something and it does work, you're like, hey, not only does it work, but this antenna that I have up in my big tree, I just used to talk all the way to Japan. I have this big antenna that I made out of just like random hunks of wire that were getting thrown out, and I turned it into a functioning antenna, and I talked to Japan with it. So,
What
all
kind
right,
of wire is this antenna wire? Is it just regular
whatever. I mean, whatever you want to use, just 18 gauge insulated wire, 12 gauge, 14 gauge.
House wire?
It could be house wiring, although you typically wouldn't. But yeah, I mean, because you want to, well, you have to decide is it going to be insulated or not. There's wire that's structurally more sound than others. There's something called copper weld, which is steel wire that with a copper cladding on it. So it has the strength of steel. And because radio frequency energy travels on the outside of the wire, it travels along the copper surface. So very low resistance. It's a little more expensive. There's wire that is, like, just your standard THHN wire that you'd use for hookup wire. I mean, I've made antennas out of 26 gauge wire. Things that, weigh almost nothing that I can just throw up in a tree.
Out of curiosity, how important is it that all this stuff be kind of open to the air? Like, would it be possible to just string a wire like down the length of my house, but like inside the attic?
The question then you have to ask the questions. It's going to couple to anything that's made of metal. To a lesser degree, it's going to couple to anything made of wood, fiberglass, but typically those are RF transparent. Shingles are typically fairly transparent. So for 7 years, actually for 13 years, I had nothing but attic antennas.
Like inside your attic?
Like inside the attic. I basically had the peak of the attic, and I ran antennas like that, and I ran other ones that ran like in a Z pattern, other ones that ran along the soffits. I had antennas that like a beam antenna that was hanging from the rafters that I could go up and turn by hand. Why not? And you don't have to worry about the weather either.
And you just use switchers to use whichever antenna you want?
Yep. I just use a switch to change it.
I.e. a mast antenna of the reasonable size with a directional rotator in the attic.
I've done that. And it was typical. I did a 2-meter beam that way, that I just had a little old school TV antenna rotator. and I just rotate it in the attic. I just put a hole in the ceiling and ran my cable up through the ceiling.
I got a question. What
Yep.
about an RV antenna? What if you're RVing and the antenna that comes in the RV, would you be able to use that?
The antenna that comes with it? No.
Yeah,
No.
I was thinking,
be
I wonder
set
how
up
you
for the
can
wrong
jerry
frequency,
rig
right?
it.
No, you wouldn't want to do that. But I mean, but if you've got like a ladder or something in the back, you basically build a clamp that clamps onto the ladder. And there are a lot of hams who are permanent RVers. You can probably very easily find online lots of ideas.
Is it better than the reason you're putting them in the attic is because of weather? And when,
It's-
you know,
It's
that,
because you're unlucky enough to have bought a house in a homeowners association, typically.
oh, otherwise the roof would be a more viable, make
Yeah,
more
typically
sense.
outside is always going to work better.
Okay.
Or you're not
Well-
trying to advertise what you have.
You know, that was part of it.
Well,
But
also
in my
some
case-
stuff I'd have to, you know, I don't know how I would sell an idea of like a 40-foot cable across some of our trees to my wife.
If you hide it well, and it's, you know, I mean, just a piece of wire, after a couple of days, never even notice it. She probably won't even notice it if you don't tell her.
Oh, my wife will.
All right, let's see. A dummy load. A dummy load is basically a resistor. It has to be non-inductive, 50 ohms, and it has to be a resistor with a big heat sink attached to it so that when you transmit into it, it looks like a perfect 50 ohm load, like basically a perfect antenna, except that it doesn't radiate any energy. It's specifically designed to convert it into heat. So if I have 1,000 watt dummy load, that means I can transmit at 1,000 watts into it and it gets really warm. So you put a heat sink on it, it dissipates heat to the air, and it's used for making tests of your equipment off the air without actually sending out signals. Okay, so now we're into amateur radio signals and modulation. So here we go. We'll just cover a little bit of this, then we'll take a short break. So we're going to cover modulation. Okay, modulation is the act of taking a radio frequency signal and changing it, modifying it to make it convey information. So let's say I had a radio wave with a frequency and an amplitude that looks like this. And it does not get turned on or turned off. It just basically operates at, let's say, 1 megahertz. Basically, this has no information on it whatsoever. It's always there, or it's always, you know, it's basically always there, no information. But what if I were to take this and make it so that it would turn off every so often? And somebody else knew what that meant when it turned on and turned off. That is then information. That information actually, this is called on-off keying. The simplest form of on-off keying, anyone know what that's called?
Morse code.
That is called CW, or continuous wave, or Morse code. That is the coding technique that we use to encode CW. And that's basically something you can hear with your ear. That would be known as Morse code, if we can go back to figuring out when it's on and when it's off. So that is a very simple form of modulation. Another form of modulation is if we take that signal and we do this with it and make it get bigger and smaller in time. And then we can basically modulate it by using, let's say, a voice or music or something, and we end up with something that looks like that. We modulate the amplitude. That is called AM, or amplitude modulation. This is actually called the envelope. And if we were to take away the carrier inside, this is called the carrier, and this is known as the modulating signal. If we were to basically fill in this carrier, we would basically end up with an amplitude that went up and down and up and down. When we demodulate something, we get rid of the carrier and we are able to recover the envelope, which is the signal that modulated it in the first place. Now, a device that does both modulating and demodulating. Modulate, demodulate. Ever heard of one of these?
Oh,
Oh,
That would be a modulator demodulator, which we also know as a modem.
Mm,
So that's where that word comes from. Modulator demodulator. Okay, we can also do something called FM, which is changing the frequency. So we can go like this and have a low frequency. And then depending on the modulating signal, we can increase the frequency, and then we can have it go lower again. And then we can go higher again. The amplitude is always the same. And in fact, when it gets to the other end, they would basically cap it top and bottom, and they would just look at what the frequencies. They'd see low, and this would be high, and this would be low, and this would be high. If they were to plot this on a graph where we had the center, they would see that it went low and that it went high. And this would have a certain amount of energy associated with it. And then what would happen is it would fill in this space from low to high. So this is, again, a frequency chart. So it's frequency versus amplitude. How much signal is there? So this is actually known as frequency modulation. The amount of change in the signal from the center frequency that you get, this is known as the deviation of the signal. This is known as the deviation of the signal, how much the frequency deviates from the center frequency. Okay, so now what we're going to do is we're going to look at our AM signal, and we're going to do this with it again, make it bigger and smaller. This is in time. So here's our modulating signal called our envelope. Now we're going to look at, we're going to sort of change gears. We're going to have our amplitude and we're going to have our frequency. We're going to have our center frequency. This is known as the carrier. Which again, is that high frequency signal inside. And then we're going to end up with these modulating pictures. This is a frequency representation of the voice that's making the thing get bigger and smaller. These are known as sidebands. So we have, since this is zero frequency and this is infinite frequency, this would be the lower sideband, and this would be known as the upper sideband. So if you've heard of AM, this is what AM looks like if you look at it on a scope, on a frequency scope. It has a carrier frequency, and it has two sidebands, upper and lower, which are mirror images of each other. So let's ask this question. If we just have a carrier signal, the carrier signal provides a frequency reference. If instead we take away the carrier and the carrier is reinserted when it gets into the receiver, we don't have to transmit it. Well, if we don't have to transmit it, we don't have to waste power making it, which means we can get rid of it. And this is actually called double sideband suppressed carrier. But you don't have to know that for this. The other thing is, since those are now mirror images of each other, lower and upper sideband, and they contain the exact same information, we can decide which one we want to make and which one we don't want to make. So instead, what we end up doing is saying we're going to only transmit one sideband, and we're going to call it upper sideband or lower sideband. And since there's only a single sideband being transmitted, we call that SSB, or single sideband. So now our signal that originally looked like this is now only that. So what do you notice about it? It takes up a lot less what?
bandwidth.
Bandwidth. It takes up a lot less space in the band, because this is physically, if you were to look at it, taking up room. And if it's taking up room, what happens if there's another signal over here that's doing the same thing? What are they doing to each other?
Crosstalk.
They're interfering with each other. That's right. Exactly right. So now if I were instead to take this and make this sideband go away and make this sideband go away, what I've now done is created more room for other people to use the exact same frequencies, or those next door frequencies to each other. Like here's another one. right? They actually would have interfered with each other using AM, but now on single sideband, they don't anymore. So single sideband has a narrower bandwidth than AM. AM fills up about 6,000 hertz or about 6 kilohertz. Single sideband takes up about 2,800 to 3,000 hertz. Now, if I were to look at Morse code, you would think, okay, well, Morse code isn't going to take up any room at all because it's just, you know, a signal that's either going on or off. Well, actually, what it turns out is that the act of turning something on and off creates information, and information requires bandwidth, no matter how, no matter, it's one of those things that math predicts and is actually true. Morse code takes up about 150 hertz. What that means is you can put a lot of Morse code signals in an area where you can put, let's say, one single sideband signal. So CW is about 150 hertz. There's another mode, which is digital, called PSK31, which only takes up 31 hertz. And that's a digital mode. And that actually allows you to send information from a keyboard at about 31 baud, which is actually a fairly, you know, it's about as fast as you can, as most people can type. And you can fit 5 of those roughly in a single Morse code signal. But at that point, the bandwidths are so small that you don't really worry too much about it. Okay, so a single sideband voice signal is about 3,000 hertz wide. An AM signal is about 6,000 hertz wide. An FM signal, this is why we don't do FM in a lot of cases, is about this wide, 15 kilohertz. So between 10 and 15 kilohertz, it is what an FM signal takes up, which is why most people do not use wideband FM or even narrowband FM on the HF bands, because there's just not that much space to use, or not that much space available. We are, believe it or not, also allowed to do something called NTSC, which is old school television, analog TV. This takes up 6 megahertz of bandwidth. So that being said, what I'm going to do is bring up this frequency chart, if it's still up on my screen. And here we go. Okay, so let's take a look at the HF band. What are the limits on the HF band? From 3 to 30 megahertz, right?
Yep.
How many megahertz are there in between those flags?
What flags?
Between the 3 and 30 megahertz flags?
27.
27. If I were to tell you that a TV signal that we're allowed to transmit takes up 6 megahertz in that area, how many could we fit?
Not many.
Not many, like 4. Yeah. And nobody else would be able to use it. So we don't do that. A TV signal is 6 megahertz, but now look between 300 megahertz and 3 gigahertz. How much room do we have there?
Tons.
Tons. We have 2,700 megahertz. A 6 megahertz signal, it's perfectly logical to put it there. So that's why we're only allowed to run fast scan TV on UHF bands and higher, because they take up a lot of room.
That's why our old TVs had like 12 channels VHF and 100 UHF.
That's exactly right, because there was a lot more room for in UHF. Okay, what do we use for Morse code? We use something called International Morse. That's for sending CW. And an electronic keyer is a device that's used for sending higher speed Morse code, where the keyer essentially makes the dits and the daws for you, depending on which way you use a paddle. And a paddle looks something like this. BY1 Venture. And this is what a paddle looks like. This is an iambic keyer. So one way makes dits and one way makes daws. And what it allows you to do is use electronics to make your signals faster and easier than you can do by hand. Okay, everybody ready for a 5-minute break?
Sure.
Okay.
Yep.
We're cruising right along. Next up is digital.
I would have to watch this again. Stuff, man, it's,
Yep.
that's some tough stuff, man.
Yep.
All right, I'm sure people have questions. Good time to ask.
Hey, Scott, I'm looking at the questions at the top of page 42.
Mm-hmm.
Which type of modulation is most commonly used for VHF and UHF voice repeaters? And
Yep.
it's FM, and then what type of modulation is most commonly used for VHF packet radio transmissions?
Yep.
But I was just thinking about what you just said, and it was talking about how the FM takes up so much more space, and
Sure
that is
does.
not appropriate for VHF or UHF.
No, no, it's appropriate for VHF, not for HF.
Okay.
Yeah, we typically don't do much of it on HF. But let me see if I've got let me see if I can find a 144390. Ooh, let me switch that. Here we go. We'll hopefully get another burst of it. That's another burst.
What am I looking at? I'm not seeing the, yeah, put it down just a little. There you go. Okay.
I'm trying to get the sound. Usually you don't have to wait too long. Make a liar out of me.
Having some offhand questions.
Scott, is your base radio set up in that same room you're at now?
No, this is my wife's room.
I was gonna ask if you could show us your setup.
I can do that tomorrow morning, or if you wait, I can maybe do it later.
I'm just curious to see.
Oh, come on. Now we're not going to hear any packet at all. One blast and then nothing. Wow. All right, I guess we'll ignore that until it comes up.
I bought this one online. I got it on sale for a beginner.
There it was. Yeah,
radio.
okay.
Do you think that's a good one for a beginner?
Like, no.
That was Packet. Okay, finally now. You want my honest opinion?
Yes.
Okay, so a Baofeng is what I call a cheap Chinese piece of crap radio. And it works fine. But their quality control is very, very spotty, and don't expect to, how can I put this? I wouldn't bet my life on it. How's that?
How far will about
Okay.
Go ahead. What was the question?
how far can you realistically talk with a Baofeng?
That is an impossible question to answer. Why is it an impossible question to answer?
How much interference would you have?
Yeah, exactly. You don't know. I mean, if I'm on top of a 10,000 foot mountain, 200 miles, right? I mean, a radio is a radio is a radio, which is why I typically don't teach anyone how to use any particular radio, because there's no point in doing so. You know, really what it comes down to is what's the application? I mean, I can take a Baofeng, a radio, if it survives, and stick it in stick it on a little satellite, run it off of a solar panel, have it 200 miles up in the air, whipping around the earth, and have it transmitting at 2 watts and be heard by people over 1,000-mile radius. Now, what I've also noticed about it is that they work just fine when they're hooked up to a standard antenna that they come with. If you happen to take it and put it on a bigger antenna, or like drive through an area where there's a lot of RF, like pagers and cell towers and things like that, the filtering, which is what they really skimp on, is such that the radio is just completely overwhelmed and can't receive anything. That's really the big difference. The fact that the filtering that's provided, which we're actually going to get to very shortly, what filtering is minimal, to say the least. So
Are you allowed to say what a good radio is
I can
for
say
beginners?
anything I want, right? whatever you find that you're comfortable using. If it's
Right, but I mean, as far as novice, like, if you buy a Samsung, you're getting a good TV kind of thing.
Well, I mean, basically, if you follow any of the standard, okay, so if you look at, if let's say you go to Ham Radio Outlet, right? And I'm just going to pick them because they have 11 stores around the country and they're a huge distributor. They also have a catalog, and if you go to
Hey,
Ham
Scott.
Radio Outlet, yeah.
I was going to add to your Bofane conversation, but go ahead.
Mhm. Well, the nice thing about them is that they can be easily paired with the Android phones and GPSs, and they can be easily programmed using free software. So I mean, there are distinct advantages to them, but again, they have a glass jaw. They're not the most robust radio in the world. On the other hand, I have 4 of them. I also have 6 of these Yaesu handhelds and a couple other miscellaneous handhelds. But now if you look at HRO, anything you get here, notice Yaesu, ICOM, Kenwood, and a couple of Chinese brands. Basically, anything you get at HRO is going to be a decent radio.
Problem is understanding what a new system might entail, just to get us going, as versus anything we could get.
Research.
That's what I was going to add.
Research. I mean, a lot of it
We have
depends.
you, the expert, right now.
Yeah, well, a lot of it depends on how much you want to spend and what you want to spend it on. I mean, let's go back to there. I can recommend like if we go here and you can pick up this ICOM V80 if you want a 2-meter handheld that's going to work just fine. It's $80. Yaesu FT4XR, that's a dual bander. They work very well. And fundamentally, internally, it's the same as a Baofeng. And notice that it's $90. So why is it $90 versus $30?
More bands,
Nope. Exactly
Better
the same. It's
quality.
exactly the same receiver.
transmitting power.
Nope. Power's the same.
Filters.
Filtering. You basically, they have spent money on building decent filters into that radio to make it a good functioning radio in high RF environments. Essentially, the chipset, it's a radio on a chip, right? It's an integrated circuit is a combination of a whole bunch of stuff on one chip. That radio and the Baofeng radios are built on the exact same integrated circuit chipset, which is basically a radio on a chip. And they work very well. They work remarkably well. But what they're not good at doing by themselves is rejecting signals that are not being listened to. So you take the Baofeng, which has minimal filtering, and it gets just hammered in an RF rich environment. Whereas the Yaesu, because it has decent filtering, doesn't get hammered in the same environment. And notice it costs almost 4 times as much. Well, at least 3 times as much. But the reason it costs 3 times as much is because they've spent the money to make it a better radio.
And a better base station as versus handhelds.
Well, I mean, the thing is, like a base station or mobile radio, depending on where you live, your radio has to be permanently mounted in your car. Like in Oregon, it has to be permanently mounted somehow in your car to be legal to use while you're driving.
But what if we're just a home station?
Well, I mean, I have a mobile rig. You know, oh, let's just stop at this one, right? There's no reason this would not be usable in your car or at home. Notice it's also $460, but it does APRS. It has a GPS receiver built in. It has a Bluetooth chipset, so you can use a Bluetooth headset with it. I mean, this is a very advanced radio for $400, right? You can also get a very basic mobile radio. So let's say like this right here. This is a single band 2 meter transmitter, 2 meter radio. It's like 80 watts, which is a lot of power, and $170. And sometimes you'll get them for even less. You'll be able to get them for $125. And again, if you typically ham radio outlet does what, let's say, Amazon doesn't do, right? You basically, if you go to Amazon, you can find like B-Tech, right? And they sell mobile radios as well. Like up here, here's a Baofeng, $59. And actually that's way more expensive than it should be. I bought one of these for $100 for like a 4-band radio once. And like this, here we go. $125 for a dual bander that actually can receive, or even sometimes a 4-band radio, right? But again, you get what you pay for. Here's one by some company called Radtel, dual band quad standby, et cetera, et cetera, et cetera. And it's $86. So what's the difference between an $86 radio and a $300 mobile radio?
Filtering.
Yeah, it's filtering, and you basically get what you pay for. So
I will say, as a new ham, a Baofeng is really convenient to start learning on.
Oh yeah.
With online forums and stuff, and you guys can actually start to learn to pick up like FM channels, radio channels, AM receiver channels and stuff. You guys can't, not necessarily transmitting, but you can practice receiving in different parts of town.
Yeah,
before you want to
absolutely.
commit to fully spending $200 on a radio. And Baofengs are perfect stocking stuffers for extra family, like for family preparedness of natural events or Mother Nature, stuff like that.
And the other thing is, if you accidentally drop one in a lake, oh well,
$30.
$30, big deal. That's right. Or
but
or you drive over.
Keep in mind, guys, the new Baofengs are nothing like what they used to be. The new Baofengs like almost aren't even worth buying at this point. They've encoded them so I don't know, Scott, you can touch on that a little bit.
Well, I mean, they keep coming out with new models. And here's the other one. They'll say, oh, we have one that's like 8 watts now. Okay.
Yeah, the
well,
8R.
yeah, but you know what? Okay, let's look at this. We already did the math, right? What's the difference between 8 watts and 5 watts? Remember that whole dB thing? Is that even twice the gain?
Nope.
No, it's not. It's 8 versus 5. It's about 2 dB. Well, you can do a lot better by getting a better antenna. And what do you know about power? Which one uses up your battery faster? In
8
fact,
watt.
8 watts, that uses up your battery on transmit 60% faster for a gain of 2 dB. So that is what we call a sales pitch. That is something that doesn't really do a whole lot for you, that sounds really good. And that's why it's important to know this stuff, because it doesn't really help you all that much.
It's another thing Amazon's good at.
Yeah, I have the 5R version, the UV5R.
Uh-huh. I mean, it's a good starter radio, right? But I would not expect that to be your last radio. How's that? It's a good first radio, but I would not expect it to be your last.
Yeah,
saw-
buy it, put 90 days on it, learn your accessories, antennas, batteries, charging capabilities, and then upgrade from there. Like I have an ICOM in my truck. I keep Kenwood in my office. I have different radios, different units for different purposes.
Yep, exactly.
I had read that the stock antenna on those, so I bought 2 of those Baofangs too, like before I signed up for this class, and I'd read that the antennas that they ship with are not very good, and that if you upgrade to like a Nagoya or something, that you'd be way better off. Is that a thing?
Well, the bigger antenna is going to be, there's less stuff coiled up. It'll give you a dB or 2 of gain. But what
Lots
I've
of fakes
noticed
out there.
What I have noticed is, personally, I think the Baofeng antennas that they sell with the radio, I think they're perfectly fine. And in fact, they're matched very well to that radio.
They're made to it.
Yeah, but they're matched really well, electrically speaking. They have enough gain that the radio does not get overloaded. A bigger antenna will very easily overload the radio.
I can tell you, if you're looking at a Nagoya antenna for $25 on Amazon, chances are that's not a true Nagoya antenna.
Yeah.
There's a lot of fakes out there that you guys got to be conscious about.
Well,
in
there's
the radio
also
market.
there's also something called a signal stick, which a lot of people in our club will buy, and it's basically a 19-inch antenna that's really, really flexible, but it's a full-length quarter wave antenna that goes in that will replace the existing antenna. People in our club really like them.
That's pretty cool.
And I think they're made here. So, okay, let's see. Okay, so this is on page 42. We didn't cover this. And thank you, Kelly, for mentioning it. The type of modulation most used for VHF and UHF voice repeaters, that would be, for instance, I get on this radio. This is an FM radio. It's an FM handheld. FM is most often used for repeaters. FM is also used for packet radio, which is what I was attempting to listen to. So packet, it will sound like, bleh. It's basically digital communications over FM radio. And it's used as the basis of something called APRS, which is the Automated Packet Reporting System, which allows a radio to be combined. There it is. Radio to be combined with GPS and be able to send information on location and speed and things like that, other telemetry data, to a central clearinghouse, and then it gets put on a map, which is then published on the internet worldwide. So, for instance, it allows you to, let's say you're having you're doing a race of some kind, or you're launching a high altitude balloon. You put an APRS transmitter on it with the GPS, and it tells where you're going to find the thing when it comes down, or how fast it's moving. Let's see. Single sideband is a form of amplitude modulation. You can use single sideband at least somewhere in every one of those bands above 50 megahertz. And why would we use single sideband? Because it is a more efficient mode to transmit and receive. It works better when the signal strengths are weaker. So we know that we call single sideband and CW weak signals. These are the weak signal modes. And notice, in fact, this says SSB and weak signal. Those are actually known as the weak signal modes. So no FM, single sideband, some digital, and Morse code. And there's room for, notice that green patch in every band above 50 megahertz. The advantage of single sideband over FM is that it's a narrower bandwidth. And I think that pretty much covers all of that. So now we're into digital stuff, which is on page 44. Digital communications mode. There are thousands, it seems, of digital communications modes available. 3 of the most common are packet radio. Then there's something called JT65, which is typically used on the high frequency bands over single sideband. And then there's another one called IEEE 802.11, also known as Wi-Fi, or that's the protocol that is transmitted over Wi-Fi. What can be included in a packet transmission? Packet, again, is a packet of information that contains a header saying where the information is coming from and where it's going to. A checksum. So basically, if I said, for instance, the message is, I am going to the store, that has 6 words. If I said, I am going to the store, and your checksum is 7, that means I am going to the store. Wait, that's only 6. I must have missed a word. That means that something was bad in my decode. I got it wrong. So maybe the actual thing that was sent was, I am not going to the store, which basically means if those things don't match, I better ask for it again. And part of that whole system is something called ARQ, which is automatic repeat request, which basically means that if I got something wrong, I'm going to say, I need a repeat. That gets sent automatically over packet.
Wait, so the term checksum is a sort of error detection?
Yeah.
Okay.
If there's more data even in the checksum, it can be used for some basic error correction as well. It can say the 3rd word was wrong, or the 3rd bit was wrong. But yeah, typically it's just used for error detection. And we actually use that when passing voice messages as well. APRS is a service that uses packet radio. It's the automatic packet reporting system. It can be used for real-time tactical digital communications in conjunction with a map. I can show you what one of these looks like by going to aprs.fi. And here's aprs.fi. And so here's a map, and here's different packet stations. And you can see, oh, look, this one's even in a car. And sometimes if you zoom out, you'll see like, oh, there's a trail. Everybody see this trail? Started up here in southern Washington, So it is southern Washington, right? Yep, I guess Portland area. And we can zoom in on it, and it's KC6YIR. And it says, okay, 66 miles an hour, 179-degree heading, 316 feet. And we can see the time that he was there. And this is basically for, he's basically got an APRS transmitter in his car identifying the station and where he is and where he's been and how fast he's going.
What is WX standing for again? What is WX standing for again?
Oh, weather. That's a weather reporting station. So they're actually transmitting over packet as well. So all of these stations are basically being reported. They're being bounced around from place to place to gateways. All those gateways eventually end up pointing to a global server. The server creates maps, which puts them on big maps with lots and lots of information. Okay. What is the kind of device that provides position reporting for a mobile station? That would be a GPS receiver. The GPS receiver tells you where you are and how fast you're going. PSK stands for phase shift keying. So we're going to think back to when we did that 2 days ago. That sine wave, that was only 2 days ago, everybody. Hard to believe, right? So because this represents where we are on a circle, starting at 0 degrees, that represents right here. This is 360 degrees. The angle that we have now gone through is known as the phase. If we are doing something called phase shift keying, what happens is that if our data that goes in to our signal changes from a 0 to a 1, for instance, and let's say that we are at this particular point, we are at, let's say this would be 0, this would be 0 right here again. We're at, let's say, 290 degrees. So we would actually be somewhere down here. We've gone through that much of the circle. When we hit a phase shift, we would change it by 180 degrees. So we would have an instantaneous change up to wherever the graph shows that we're up here. Well, so that would be up here, and we would continue going right here. So that change right there is a phase shift, and that would basically represent a change of data, and that's known as phase shift keying. It changes the phase of the signal. We can do binary phase shift keying. This is binary because it's 2 choices. We can also do quadrature. So a quadrant is a 90-degree section. So quadrature phase shift keying is where we can shift by 90 degrees at a time.
When would you use these shifts?
You can use them to, for instance, quadrature, and it can indicate that you have one of 4 different things. In other words, you could encode 2 bits at a time. To say that if I change from 0, 0 to 0, 1, that would be a 90-degree phase shift. If I change from 0, 0 to 1, 0, that would be a 180-degree phase shift. If I changed from 0, 1 to 1, 1, that would be a 270. I could, for instance, come up with a coding scheme where then the other station would see, oh, okay, I saw a phase shift and I was able to tell what the shift was. So I could actually say that, oh, it was a 90-degree shift. It was a change from a 0, 0 to a 0, 1. 2 bits at a time, for instance. So it just allows you to transmit potentially more data. The nice thing about it is that it typically does not take up very much bandwidth. A mode called PSK31 transmits at about 31 baud, which is 31 bits per second. And it has a bandwidth of about 31 hertz, which is really, really narrow. Takes up almost no room. Digital mobile radio is DMR. And this is a technique for time multiplexing 2 different signals on 1 channel. So remember we said an FM channel takes up about 15 kilohertz. Well, in theory, you could split it up so that there's the low part and there's the high part, and then you could split them in half, but you'd basically, kill your fidelity, and you'd have to come up with a different transmitter for each one. What we do is we say that for part of the time, these guys get to use it. For instance, the red channel gets to use it. And then once their time is done, the green channel gets to go. And everything is time synchronized so that the red channel people don't hear the green channel people, and the green channel people don't hear the red channel people. And that's known as time division multiplexing. And that's what digital mobile radio does. So it allows 2 different voice signals to exist on the same channel. A talk group on a DMR repeater basically says that each of those channels, this will be, if you want to operate as part of the green group, you would set up your radio to operate as the green channel. If you want to operate in the red channel, you would set up your radio to operate as part of the red channel. So you'd basically set up your radio to operate with them as part of what's known as a talk group. And in order to join that talk group, you program your radio with the group's ID or code. It could be something as simple as green, or it could have a value like QCX72. That's just something that's defined by the group that allows your radio to synchronize with all those other people. Digital software in the WSJT suite. So WSJT is something that was invented by Nobel laureate Joe Taylor. He's a Nobel laureate physicist. Joseph Houghton Taylor, physics. So this is, sometimes people get into hobbies that are very interesting to them. And so this is, if you meet him on the air, this is Joe, right? If you happen to meet him in academia, he's Nobel Prize winning astrophysicist Joseph Houghton Taylor. Well, he is also at Princeton University, and he took it upon himself to say, I would like to create a new mode that I could use to do moon bounce. And I would like to make it so that I can operate at very, very low power levels and and make moon bounce available to people who don't have really big antennas. So what I'm going to do is I'm going to create a brand new operating mode where the signals take a long time to send because the moon's not moving very fast. And I'm going to send very, very, very slow data with a lot of redundancy and a lot of error detection. And he called this mode, because his name is Joe Taylor, weak signal Joe Taylor, WSJT. And one of the modes is JT65. So that's one of those things that's used for moon bounce. Another one is that since we have these weak signals that are then propagating over through the ionosphere on different frequencies, we can actually pick them up from station to station on the surface of the Earth. And it takes almost no power to determine what propagation looks like. So they're used for propagation beacons. And the other thing is that we can also, if you change the signals so that the data rate is very high, you might have a 15-second meteor trail that's made as it shoots through the sky. This is an ionized path. And if you can send the data really fast, you can send a signal up, it bounces off a meteor trail and bounces back down. That meteor trail goes away. Somebody said, okay, I got it. I'll just wait for the next meteor trail. And I'll keep sending stuff, and eventually maybe one will happen and I'll get a path that works. So that whole thing, instead of taking, let's say this is like 3 minutes to make a contact, this is like 5 seconds. So he created all these different really cool digital modes with lots of error correction that are able to operate on these really in these really interesting ways. One of them that has come about is something called FT8, which is sort of a hybrid of all the JT modes. This only takes 15 seconds to make a contact. So basically people operate at 15-second intervals, up, down, back, forth. So it's faster than the other modes, not as fast as the meteor scatter modes, but it's really good for working weak signals on the Earth. People use it a lot. If you turn on the bands, you'll hear all over the world a lot of those signals, and that's known as FT8. Broadband Hamnet, also known as ARDN, AREDN, is an amateur radio network using commercial Wi-Fi gear with modified firmware. Again, that's where we find all of our repurposed Wi-Fi routers. A lot of ubiquity type stuff. Okay, we're into electrical safety. All right, this is something that is a good idea to cover. We have to do it because it's really important. Okay, health hazard presented by electrical current. 100 milliamps is more than enough to slow your to stop your heart from beating. Even 10 milliamps is enough to make your heart stop. So health hazard caused by electrical current flowing through the body. It can cause injury by heating tissues, can disrupt the electrical function of cells and cause involuntary muscle contractions. I once got a 250 volt DC shock. My hand started here and it ended up way up here, and I don't know how it got there. In the United States, the green wire, we're on page, I believe, is it 49? Somebody want to verify that?
Yeah, that's right.
49, okay. In the United States, the green wire connected to the 3-wire electrical plug, the round plug at the bottom is the ground wire. That is the green wire. And that is a standard everywhere. Another thing that's largely standard on those plugs is the black wire is the hot wire and the white wire is the neutral. The neutral is typically grounded in a lot of systems, but the green wire is ground and it's actually hammered into, it's actually connected to a stake that's typically driven into the ground outside your house. A good way to guard against electrical shock in your station, use 3-wire cords and plugs for all AC equipment. Connect all AC powered station equipment to a common safety ground and use a circuit protected by a ground fault interrupter. Those are those things in your bathroom that say test and reset that always seem to trip when you plug in your hair dryer. And the reason they trip is because they measure the difference between the current going one way and the current going the other way. If it sees a difference, it says, oh, the current must be going through somebody and I'm going to trip out and save somebody's life. So don't get angry at your ground fault circuit. And sometimes, yes, a transmitted radio signal will fool a ground fault breaker and cause it to trip. I've had that happen dozens of times in my life. The purpose of a fuse is to interrupt power in case of a current overload. Why should you never put a 20-amp fuse in place of a 5-amp fuse? Because somebody has engineered that circuit to take a 5-amp fuse and all the wiring is designed for a 5-amp fuse. And if you put a 20-amp fuse in, you could actually cause something to catch on fire. A fuse, excuse me, a fuse or circuit breaker should always go in series with the AC hot conductor. Once again, the AC hot conductor is the black wire, which is in the wall.
The narrow plug.
Hmm?
The narrow plug.
And also the narrow plug. That's right. In a power supply that's turned off and disconnected, you can get an electric shock from a large capacitor. I once actually did that. I actually had a 9-volt capacitor, a 9-volt battery, hooked it to a really big capacitor about the size of my forearm. And I was 10 years old at the time, and I discharged it using a pair of screwdrivers, which I then touched together. And I caused the chrome vanadium steel on both screwdrivers to temporarily melt. So a big capacitor can give you a shock. It can also be the basis for something called arc welding. A 12-volt storage battery, don't short the terminals together because a big short can actually ignite hydrogen gas. It can also cause a lot of heat to be dissipated in the battery, which can cause it to explode. And because a lead acid battery contains sulfuric acid, one thing that can happen is you get showered with sulfuric acid, which is never a good sign. Okay, antenna and tower safety. If you're putting up an antenna tower, watch for overhead wires because that's a way to kill yourself. If you are working on a tower or an antenna, make sure that if anything falls, nothing can come within 10 feet of something that's energized. Don't use a utility pole to mount an antenna unless it is your utility pole and nothing else is on it, because first of all, it's not yours. Secondly, those power lines that are up there are typically going to be running at least 7,200 volts, sometimes 12,000. It's enough to really ruin your day. If somebody touches an antenna while transmitting, you can get something called an RF burn. Remember I said that radio frequency energy travels on the outside of conductors? If you happen to touch a conductor that's carrying RF current, the current will travel along your finger or your arm until it finds a way in, and then it will make a nice little puncture hole, which hurts a lot. So be careful. When should members of a tower work team wear a hard hat and safety glasses? At all times when work is being done on the tower. A good precaution to observe before climbing a tower is to put on a carefully inspected climbing harness with a fall arrestor, which is kind of like a springy thingy, so that if you do fall, the fall arrestor will slow you down so that you don't just get slammed to a stop. If you happen to accidentally use it in a fall, you need to replace it. Under what circumstances is it safe to climb a tower without a helper or an observer? The answer is never. If you get stung by a bee and you have a bad reaction, or if heaven forbid you have a heart attack and you're up on the tower, you will be stuck there and no one will know. Which of the following is an important safety rule to remember when using a crank up tower? Crank up towers are not designed to be climbed in the extended position unless you have mechanical stops in place. Otherwise, they're meant to be retracted and worked on when everything is down. A turnbuckle is a device that you use to tighten a guy rope or guy wire. You basically rotate it and it pulls tension on both sides of the guy rope that it's attached to. Wind will typically tend to vibrate it and will tend to vibrate it looser and looser, in which case you have no tension on your ropes anymore and your tower will come crashing down to the ground. So you put a safety wire through the turnbuckle and you anchor it so that it can't rotate in the wind. A gin pole is basically a little crane that mounts to the top of an antenna tower. And the reason that you would use a crane with a pulley is so that when you're hauling something up that weighs 80 pounds, you can pull down instead of having to yank it up. That's known as a gin pole. What establishes grounding requirements for an amateur radio tower or antenna? That would be local electrical codes. Follow NEC and your local codes. When grounding a tower, use a separate 8-foot ground rod for each tower leg bonded to the tower and to each other. Don't use sharp bends when installing lightning protection because lightning likes to go around smooth curves and straight lines. If you give it a sharp bend, it will jump off of the wire and find another way. When installing ground wires on a tower for lightning protection, you want to also keep those wires as short and direct as possible. And all of the external ground rods that you use on a tower should be bonded together with a heavy wire or conductive strap. Finally, if you have lightning arresters in your coaxial cable, if you think about coaxial cable, there's a center conductor and there's a shield around it. Well, typically what's going to happen is if you get a really big lightning strike, it will jump that gap. So what you do is you intentionally give it a gas-filled tube that normally is an open circuit, but if there's a lightning strike, it will ionize the gas in the tube and give the electricity an easy path to get to ground. For hopefully getting the lightning gone before it gets down into your station and blows up your equipment. A better idea, however, is if you know that there's a thunderstorm coming, you just go and disconnect everything. So just literally disconnect everything. All right, and we are on the last section for today, which is RF hazards and radiation exposure. And I know it's 12:08, almost there. Okay, VHF and UHF signals are non-ionizing radiation. If we were to look at our chart right here, when we get over to ultraviolet and X-rays, those are known as ionizing radiation. Those photons carry enough energy to cause genetic damage to your cells. Radio energy, it can cause heating, think microwave oven, but it can't do any genetic damage. So it will not knock your DNA into pieces and cause genetic damage to your cells. 50 watts peak envelope power. We covered what an envelope looks like. The envelope is the outside of the modulated signal. You're allowed a peak power of 50 watts at the antenna before you have to do an evaluation, although it's recommended that you do one anyway, no matter what your power level is. Well, you can use any of these methods: computer modeling, field strength of using calibrated equipment, or FCC OET Bulletin 65 to figure out if your station is safe or not. Well, FCC Bulletin OET 65 is a pain in the neck to deal with. However, there is there's a guy who came up with this website, which is always great to have. And I'm going to put this in the chat as well. Here's the chat. Okay, now I'm going to share the site. Notice RF exposure calculator. This actually implements the FCC OET Bulletin 65 in a very simple way. So let's take your average mobile station, average power at the antenna, 25 watts. Average gain, notice there's dB, but it's in dBi. It's a vertical antenna, so we'll say 3 dB. Oops. And distance from the antenna, let's say that somebody's walking by the car, you're about 2 meters from it and transmitting at 146 megahertz. Is this safe, yes or no? What we find is that, okay, given the parameters that we put in, we have an estimated power density of 0.2541 milliwatts per centimeter. Can everybody see that okay, or should I zoom in a little bit? Let's make it bigger. Okay, now what this also means is that given the numbers that are in FCC Bullet No ET 65 Supplement B, here are the safety limits for a controlled environment. So we're well within the limits for a controlled environment. Controlled means that you have control of the environment. Let's say you put up a fence, or you put up a warning sign or something like that. Uncontrolled means that the general public is not aware of what's going on as they walk by. So if you have a sign up that says, stay away, radio operations in use, keep your distance, that becomes a controlled environment. If you don't, you just are sitting in your car operating at 25 watts, that's uncontrolled because somebody might walk past your car. In which case, oh, look at that. No, it's not in compliance, which means there's a couple of things you can do. Well, you can lower your power. If I go back here and I lower this to, let's say, 15 watts and go, well, now look at that. Now we're safe because we're operating in an area where the power density is now safe for somebody to walk by. So it's good to know how to use this device, how to use this table, how to use this website. The definition of duty cycle is basically the percentage of time that you're transmitting. And it affects the average power that someone's exposed to. For instance, if I were to transmit at, bye Jim, if I were to transmit at 100 watts for 5 minutes and no watts for the next 45 minutes, my average power would only be 100 watts, but only for 10% of the time. So my average power would only be 10 watts. And that's important because it goes into those calculations as well. So if the averaging time is 6 minutes and you're transmitting for 3 and not transmitting for 3, that means that you could actually run twice the amount that you would otherwise run for that time that you're transmitting. Why do exposure limits vary with frequency? The reason being that we tend to be electric things, right? We're full of salt water. We tend to radiate, or we tend to absorb energy as well, and we tend to couple to antennas. So we actually absorb energy based on frequencies. We actually maximize that absorption at 50 megahertz, which is why the exposure limits are lowest on the 6 meter band. So what affects the RF exposure of people near a station? Frequency and power level, distance from the antenna to people, and radiation pattern of the antenna. Radiation pattern is very important, isn't it? Remember yesterday we showed that little Wi-Fi system. So here's our beam antenna with 400 milliwatts and a forward gain of 30 dB. That made an effective radiated power of 400 watts. I would not want to be standing in there, even though it's a teeny tiny transmitter, because it's effectively the equivalent of 400 watts.
Wouldn't
Okay.
it be like 400 watts in basically like a pencil point space?
Yes, but if you happen to be standing there, I still wouldn't want to be there. That is not a place I would want to be. So I would be behind the antenna. Okay, so if you find that you're in excess, you can relocate your antennas. You can also transmit less. You can decide you're only going to transmit at night when there's nobody around. And to make sure that your station stays in compliance with regulations, whenever you change anything, you go ahead and recalculate it. You just go back to the website, recalculate it, print out your forms, and you're good to go again.
I'm sorry, one question.
Yeah.
That calculation, would you keep that in your logbook?
I would. I would actually, okay, so we actually run a station over at the Eugene Science Center here. And one of the things that I did when we put in the station was I said, okay, well, here's our equipment. It's gonna be worst case. Conceivably, we're gonna run 100 watts. It's a dipole antenna, so 2.2. And the area to the interest, the antenna's on the roof, so people are about 5 meters away from it at 28 megahertz, because 28 megahertz is worst case. So here we go. If we're transmitting at peak power all the time with people 16 feet below the transmitting antenna, then here's the power level, 0.1353, worst case, and we can go all the way up to 0.23. So let's say that, okay, let's say that we're only, let's say 3.5 meters, so 10 feet above. Okay, so what that means is we're now, if we're operating 100 watts all the time from the center of the antenna, we are now in excess of if the antennas are only 10 feet above the people. So one thing we can look at, we can raise the antenna another 3 feet and it comes into safety. The other thing is that nobody ever transmits. Notice it says average power. No one ever transmits 100 watts all the time. That would kill your equipment, first of all. So really, let's say that we're transmitting 50% of the time. Well, then we're legal again. So
Is that at the science factory, like the kids science center, like
It
behind
is.
Dodson Stadium?
it is. And in fact, here's the calculation. So 50 watts, 2.2 dB, 3.5 meters. We say, okay, well, so we're safe. But now let's go and again, switch it to 100 watts. And now, no, for an uncontrolled environment, it's not safe. And I would consider people just walking through the museum to be an uncontrolled environment. We were to change it to 6 meters. We're really above the limit. But again, nobody transmits an average power of 100 watts. And in fact, the worst case would be, you're having a 100-watt conversation and you're talking half the time. So let's say that it's 50 watts average. And then once again, we're legal again. So by playing with those numbers, or let's say we put in an amplifier and we had a 500-watt transmitter. This better be, so this is clearly not safe. But let's say that instead we were to raise the antenna to 7 meters above the ground or 7 meters above the people. Well, we're not quite there yet. So we'd have to go a little higher. Let's make it a little higher. Let's make it 10 meters. So we put in a 35-foot tower or 40-foot tower. And guess what? Now, even if we're transmitting at full power all the time, we're still legal. So that's where it's, you start to get into, RF safety and what's safe and what's not, because, I don't want to hurt anybody else. I don't want to hurt myself. It's supposed to be fun. I certainly don't want to make myself sick. So, and again, it's a cumulative effect of heating. It's not like you're going to do genetic damage to yourself. Certainly don't want to cook yourself. So now here's the other question. I take this radio. How far is this radio from my head?
Very close to radiating.
Very close. So here we go. Let's go share that again and just go through. And I'm sorry if I'm running a little bit late. You guys can go if you have to, but this I find is very useful to do. So let's say that I'm averaging 2.5 watts and it's a quarter wave. We're going to say that it's basically a dipole. The distance to the antenna is about 1/10 of a meter at 144 megahertz. Here we go. Look at that. What do you see?
You're getting cooked.
You're getting cooked. Yeah. It's not safe for you. It's not safe for anybody. It's not safe for anybody walking by at that distance. So if I'm using my radio, do I hold it? I can sometimes hold it like this, so maybe that increases the distance a little bit. The other thing you can do is if you're going to be operating at high power is you get a speaker microphone, right? And you can hold the radio up here. Besides getting the antenna up higher, it adds about, 1/2 meter to 1 meter of distance. So now let's say it's 0.7 meters. And look at that. Now it's safe again.
Hmm.
So, that's the other reason why, okay, if I can, I would like to run, let's say, a 1/2 watt average, which is, like a 1 watt transmitter. And let's put it back at 1/10 of a meter from my head. It's still not safe, but it's closer. So now let's turn the antenna the other way. For a controlled environment, what this means is that if I know what I'm doing, it's okay. For the general public walking by, it's still not okay, but nobody's going to get that close to me. So if I'm aware of what I'm doing, then it's okay. The other thing that it means is that if I take that 1 watt transmitter and I listen more than I talk, my average power goes down and it becomes safer. Still not quite, yeah, I mean, that number basically is now okay for everybody.
I would put that document in my logbook.
Yep. I would, and actually at the museum, not only did we run those numbers, but we actually put it up right over the station. We actually taped it up there and said, here are the numbers. We did the safety evaluation. If anybody wants to see it, these are using the FCC guidelines. It's safe for everybody. And if we change anything, we have to do it again.
Was that in one of the side rooms, kind of off that main corridor, or
Yeah, it's in the
go there a lot when my son was little?
It used to be the computer lab. And then it became the discovery room. There's a whole bunch of fossils and stuff in there. All right. Any questions from today? I see a hand up. Maybe it wasn't a hand up. No questions? There's a hand. All right. Any comments before we go? Any thoughts? Any questions about exams?
Yeah, I do have one. Is tomorrow sort of a summary day of everything, or is there no information?
No, tomorrow's new information.
Ah.
Yeah, tomorrow's, well, because we haven't done how to build a station and how to deal with interference. And we haven't done operating procedures.
Ooh, yeah.
Rules
Okay.
and regs. Yeah.
Would you say that if you can consistently be pass a practice test, you should be fine for the actual test?
If you're getting 80, 85, 90%, you'll be fine. I mean, because actually the exam that we do is, you may recognize this. Is anyone using hamstudy.org?
Yes, I am.
Okay. Do you recognize the look and feel of this website? It probably looks very much like this. Notice it's by signal stuff.
Yeah.
This is the exam site. So if you're used to taking practice exams over here, this will look very, very, very similar. So, the look and feel is almost identical. I'm not going to say it's identical, but it's very similar.
What's the format of the exam? Is it essay questions or multiple choice or what?
Have you taken practice exams?
Well, here's my theory. I'm set to fail this exam, but I thought it was better to try to understand the material rather than just memorize answers.
Yes,
So
but have
no,
you taken practice exams?
I have not.
Okay, what I would do this afternoon is I would go to that website and I would practice a few times, at least a few times. I mean, you could take 100 practice exams and eventually you will see all the questions. Just, I mean, it's all multiple choice and you will recognize a lot of the questions.
Practice exams are a good tool.
Really good.
I'm taking 3 or 4 of them a night before bed.
Yeah.
But what about my logic of there's too much brand new material and I need more time to understand the material. And so I feel like it's a waste of my time to just memorize answers that will just be floating around in my head, disconnected to any understanding.
Well,
how about that for logic?
but at this point, they won't be disconnected just knowing what, just doing what we've already done, there won't be a disconnect on a lot of them. Are you scheduled to take the exam on Friday?
I am.
I would definitely prepare. I mean, if you're not ready for it too, that's why, I send out a note that says, hey, if you're not ready to take an exam, Kent can reschedule you. But, I mean, that's why you really do want to be working on it, practicing.
Right. How long are your recorded sessions going to be available online?
I never take them down.
Okay.
Yeah, so let me go ahead and stop now that I think about it.